Just, oops. Is it okay for the picture, everyone? Thank you. Okay, good morning, everyone. Welcome to École des Ponts. And thank you for fighting against the strike in France. But you know, a visit in France is always coming with cheese, red wines, and strikes. But at least you have a good weather for the today and tomorrow. Welcome for people on site. Obviously, welcome also for people online and who couldn't join with us. So we're going to spend 2 days together at École des Ponts mainly for the defense of all the Capstone projects, which is a big achievement for all of you, and congratulations in advance for all of you, and also for your graduation ceremony tomorrow afternoon. Just so I put the calendar here of today, and I have also the one for tomorrow. So we'll start this morning with 2 Capstone, Nomon and CEH. And in the afternoon after lunch here, so the lunch will be just outside, we'll have 3 Capstone projects, INECO, ARUP, and ISA. So for this morning session, we will have a representative of each institutions for the jury of your Capstone project. So we have Alexandro Vadova from UPB, Alex from UPM, Christophe from BME, and Jérémy from École des Ponts. And that will be the jury of your Capstone. You have 1 hour in total, each group. So basically, as we have done the rehearsal in June, maybe a maximum of 30 minutes of presentation and question and answers just after that. And we have like maybe 10 minutes break just to adapt if needed. Just some information, practical information. You all have a tag with your name, so you have to keep it until tomorrow. I mean, you have to use the same tag tomorrow. Okay, don't lose it, please. Second thing, you will have attendance sheet to sign for today and tomorrow. So we are going to prepare them, and we will put them outside. So don't forget to sign the paper. It's important. We are obliged to ask you that. Last thing, for tomorrow, we won't be. So today we are spending the full day at this building, in this lecture hall. Tomorrow it won't be the same as you have seen in the file I sent you last time, but I prefer to put it again to be sure that you are all aware of that. So yeah, I don't have a laser, but I think I can use a mouse. So today we are here in Bâtiment Bienvenue. And now you know the way to come here, so it's easy. Instead of going to Bâtiment Bienvenue, you go to Bâtiment Coriolis, which is here. So that's for tomorrow, okay? And finally, so tomorrow morning and afternoon, and to be the same building. And I don't know if I sent to you the address, but I think I did, for the restaurant for tomorrow evening at Maison de la Radio. And the name of the restaurant is Radio It. And I mean, I don't say it now. I don't want to spoil the fun. So you will see the restaurant tomorrow by yourself for the gala dinner. I didn't say to you, but it's there is no specific dress code. Don't worry. I think we say something like casual chic or casual thing like that. Yeah, that's all. So don't worry about the dressing code. Thank you again. I don't know if you have any questions regarding the organization so far. Feel free. And if not, we are going to start with the first Capstone project, with the Nomon project, with Ali and Ash. And first of all, I ask Alex to come and just to introduce the partnership with Nomon. And obviously, I forgot, but I thank all of you to come, learners, mentors, academic, faculty members, everyone, obviously. Thank you, Alex.
Thank you, Mate. And as just Mate has said, thank you all for coming. You know, we are already aware that this is an effort to make some room in your agendas. It's difficult for all of us to get it. And also I would like to introduce the partnership we have been enjoying for the last 2 years with Nomon. Nomon is not only a company database entrepreneur, but it's also one of the key companions that we have had in this project. Since the very beginning, we started to think that this master and the whole digital twin project should be a partnership between universities and companies. Otherwise, the role that we have here, that it is implementing digital twins into our real world, was going to be not possible, because it could end it just being a faculty thing, and that's something that we didn't want to happen. That's why we ask different companies to join us in this trouble, in this journey, and I am glad to say that they were eager from the very first minute. They were so eager to join us in this project that they have been one of the main reasons that some of the specialization courses have been developed. Actually, a former partner from Nomon, Javier Burgueza, was one of the main responsible for developing one of the modules that you have already enjoyed in the specialization courses, and also he left Nomon some months ago. He left his heritage into really good hands. So for me, it's just a pleasure to ask the Nomon team to come here to the stage and present us the work they have been carrying out for almost a year. So thank you very much for your attention, and please, Alison and Ash, come here. Thank you very much.
For the slide, you can use the mouse or the arrow. I can. Okay. You can. It is this one, I think. Yeah, you can use the microphone or this one. You can try. Put it close to your mouse. Don't forget.
So good morning. We are very happy to be here and share with you our results of the Capstone project. So let's get started. We were wondering about how to start our presentation. So the first thing we think was to looking for some information about our topic. There we look and find different things, right? Like infrastructures, smart cities, and different factors, but we are looking for something more specific and asks about the principal components. And again, smart city, planning, data, mobility, etc. So let's do it more specific. Key elements of the urban digital twins. This was really, we find that one main factor is missing in these results. So, and the final try, we looked for objective of the urban digital twins. And here we find something special, something important, that is the main of the citizens in the urban digital twins. And there, just for why not, we asked to ChatGPT for the same, and as always, say a lot of things, and we asked just for a summary. And again, the same. Many factors, but one important thing is missing: interoperability, simulation, devices, data. But the main factor and the question that we ask is people, right? And we think that our supervisors made the same question when they was motivated on, that is the motivation for why they proposed this project. So our supervisors, what we want to do here is to say, what do you can implement for improving your urban digital twins? And we want to give you that tool for improving your urban digital twins models. So our supervisors are Natalia Sobrino and Pablo Ruiz. My classmate is Ash ND, and I am Alison Fernandez, and this is our Capstone project.
Thank you. So So it's a brief outline of our Capstone project. So first we will define our project, then we'll talk about the project development with methodology and technical implementations. Then Alison again will talk about the results and discussions. And finally, I will conclude with the outcomes and as concluding remarks. So basically, so we all know about the digital twins, but we are, as Alison mentioned, we are focusing on the key part, the fundamental part of this UDT, the people. So because whatever model we built it should be for people, but the people is the number one component. When we talk about the urban planning or urban digital twin or infrastructure planning, so that's the motivation for undertaking this fantastic project.
The screen is not shared. I'm very sorry.
Yes.
Really, really sorry. I thought it was shared, but it's yeah. I think it's fine. Sorry.
This one? This one, yeah. 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 So, yeah. Good. Noise, there is a mismatch.
We can say the same screen that we are
No.
on this, in
The different, there are different.
it's different.
Where is it? Mouse? Where is it? Mouse? Oh, it's here.
No, yeah.
This fine?
Yeah.
Yeah.
Sorry. Sorry again.
Thank you so much.
Okay, thank you. So basically, as we have mentioned, that the people is the core of this core is of any urban planning or urban digital twin. So it's not an option. It's basically a necessity that people must be incorporated into urban digital twin. We should provide a most important layer is the human-centric data into the urban digital twin. So that's the our motivation, and the justification is also is same that we can build UDT without human data, or we can build with the human. So that's the difference you can see in the picture. We are developing this project to achieve some goals because. Our model is not, we can, at this stage, we can say our model is not comprehensive, but it's a very fundamental tool which can meet basic requirements, and more data layer can be injected in future to make it more comprehensive and better. So our overall objective is to develop a model that can predict human presence in urban areas, and at the same time which can be which can deliver the human data into the urban digital twins. So in basically our whole model comprises four stages. First we will integrate different types of data, the dynamic data and the static data. The dynamic data, we are talking about the human mobility, and static data, we are talking about the land use information, cadastral data, demographic information. So we will try to integrate all these types of information to build a model database. And then we apply different algorithms to to predict the populations by building a relation between our target variable with the independent variables. Then we also try to explain how this model can be integrated into urban digital twin, and with how our model can be used in our in test cases, like in different urban characteristics, like the park, like transport hub, or like an stadium where mass events are gathered. So in our model, dear audience, in our models, we have used Madrid as a case study because as you all know, it is not only because it is one of the largest city in the world, and at the same time, the Madrid City Authority has developed a strategy for digital transformations of the Madrid. The full city will be digitalized, and they are trying to boosting the intelligent and smart management. And also most important, they are also trying to develop a tool, a very useful tool, adaptable tool, so for local municipal authorities, so that they can use this tool for for decision making and urban management purposes. So regarding the development phases, basically our model, we have five phases. So first we have identified the problems that we have already discussed, that we consider the people as the fundamental, as the core of any urban digital twin. So we only focus on the people. And then we have defined the project, and the technical implementation is basically the heart of our project. Later we will discuss more about technical implementation, but I'm talking about also the MVP, that minimal viable product, because our model is, we can say it can meet the requirements, and at the same time it is adaptable. It is adaptable. It can be improved by injecting a lot of data, injecting other types of data. We will also talk about the limitations in later stage of our presentations. So at the first stage, we have been collected data. Thank you, Norman and Pablo, that we have collected the GPS data, mobile network data from them. And we also collected all types of data, land use information, cadastral data, and sociodemographic data from available public website, especially from Madrid City Council. Then we have prepared processing the data, because as it's a traditional stage, but we try to remove the outliers. We try to investigate the pattern of this the data, and then we perform the EDA. We also try to see the relation between different variables, the independent variables and the dependent variables. Here, basically in our model, the GPS data is the baseline, and we have considered GPS, the number of GPS app users, as a proxy of the population density in a particular area. Then the rest, we also do the feature engineering. Because we have transformed the data from the raw data to more informed data, that from there we can see the pattern, we can develop the relation between different variables, because we also try to make data, we make a uniform code, because we have collected data from different sources. Each source are following their own way of coding. So then we do our modeling, because we apply different techniques, and we select the best one which can predict the human population, and finally we do the validation. So our Ali will continue from here.
Okay, this is the technical but not boring part, and we will start with the data, describing the data. And our main basic data set was the GPS data, because it's a huge volume of data, and have the information about how many users are in one place. And this is information is by coordinates, latitude and longitude. We, using the cadastral information, we be able to plot the register by census tract level. Census tract level is like the 4 level in what you can represent the geographical and administrative information, I think so, about the how a space is splitted. So the other both data sets that we use was the sociodemographic information from the AAN. The other one was the census tract, which the land use, sorry, which give us the information about the different use of the land use of the geographical place that we are using as case study. With the main, the more relevant from this data is that we can find the we can find information, and we can be able to answer in these questions. From the cadastral and GPS data, we can answer how many users are in one place, and with the cadastral, we can put where is the place. With the sociodemography, we get the human characteristic about the people that are in the place, so we can answer the who question. And with the land use, we can answer the why. The people is in that place because they are working, because they live there, because they are, I don't know, making something, one hobby or something like that. And just for understand the data, we did like preliminary spatial analysis. And the first one was a heat map where we can see where is the main population concentrated in the city. And also we try to understand the patterns in mobility for 1 month in the case study. So as we can see in the graph, for example, is about specific information, how the people move inside the place. With these insights and with this analysis, we was able to understand how the data as how the data was how to describe the data, what the data we were using. And then we start with the pre-processing part. So in this part, we want to highlight the main important tasks, and it was like a standardized geographical system because the different data sets that we missed was in different geographical systems. And then we merge by using the same identifier in the 4 data sets. Then we resolve the problems like missing values or null values that we find in the table. And the final, we define the target value and the explanatory one that we will use for the final model table. So with this information, we achieve to get the final model table that have a 40 variables, which is split from different uh, factors like temporal, spatial, human characteristics, and land use characteristics on spatial characteristics. So after the pre-processing, we go with the future engineering stage. And in this, we arrive to basic tasks. The first one was to see how the original target variable was distributed, and we find that this has a circuit at the left. So we apply a logarithmic transformation in order to have a normal distribution because the models function better with this distribution. Then related with the temporal variables, we decide to create two new variables, one for describing the day number, that is like, for example, if Monday is number 1 or number 0, it depends what is the programming language that you are using. We we use Python. So in this case, Monday was number 0. This is a mistake. Monday was number 0, and Friday was number 4, and that's and that. And also we were using the hours in interval hours, but we designed to transforming this in one exact value. So for example, in one range, we take the main hour, and that's all. So with these transformations, we get 3 new variables for the model table. And with this complete model table, we made the correlation part, the correlation matrix, in order to see how the variables are correlated and what variables are really important for our project. In this part, we find something curious, like for example, the line use for urban is negative correlated, and we can explain this from different factors, like for example, that more people live in one area doesn't mean that the people stay in that area the majority of the time. Maybe the people live there, but spend more time in the place where they work or something like that. So this was very interesting to find why we obtain this correlation. For example, the population is almost obviously we can hope that to find more people where more people live, right? So where the population is high, we will wait to find more people there. And something related with the average age, for example, is that like the GPS area, GPS data is taken for apps. So this is very related with the users that use that ads. So we can also expect that the younger people use the ads that elderly people. So we find this correlation like it's almost normal. The last one, for example, the land use for transport have a positive correlation because transport places are places where people go daily. People have like patterns with these places. So this is very like normal correlation too. And that with this analysis, we be able to understand how the complete model and the complete variables have a relation between them. After this, we go with the modeling part, and we find that this problem is a regression problem because we are trying to predict continuous numerical values. Like with everything in the life, we start with the basic model and go with more specific model or more expertise models. So we start with the linear regression, try with decision tree, and the final try with a random forest model. That is the summary of the amount of variables that we use and what is the definition for each set. And when we apply the model and training this, and we find these results. For the results, we can see that linear regression is a really bad a model that doesn't work for us. Decision tree was really good. Also, we tried to another decision tree, which is a limited one, but the results doesn't good enough. Then we tried the random forest, and we achieved the best metrics value for the random forest, which is normal because random forest is like a join of many decision trees. So if we find a good result for decision tree, we can expect to get a better result for random forest models. So when this was everything solved, we get our results. Our results was this flowchart step by step. When we start from the very beginning with the data preprocessing, we pass from the future engineering. We develop the analysis of the variables. We arrive to the model testing using three different metrics. We get the we made the selection of the model, and the final we save our model. So our model was the random forest. For validation, we select a specific census tract. We analyze how the original target variable was the distribution in this census tract, and transfer then in order to get a more normal distribution. In this census tract is located the Moncloa interchange in Madrid. This is the interchange is very relevant in Madrid because concentrating a very high number of passengers per day, so it's an interesting study case, and we apply your model. The result was in the table at the bottom, and as we can see, was a very good result. So also we just for to make a better idea about the variables relationship, this is the importance graph, and this is say what is important for the model, what is the most important features to describe the target variable. And we find that census tract area, of course, because if the area is bigger, more people can be here there. The hour, the population, the number of the day, the salary, and the others that have almost a depreciable importance in this case. So also for the use cases options, in order to propose, I validate the model with other use cases, we propose beside additional to the transport area, we propose to use an open or public area, because we can see different scenarios and we can see different contexts in a public area that in a transport area. For example, in a transport station, the access is controlled, but in a public area, this is not controlled, and the spaces has a human behavior like very, very variable, right? Because it depends in a lot of different data, the weather, I don't know, if it's raining, if not, is the month of the year, for different things. With this use case, the more important is to capture irregular or difficult patterns or predictable patterns in the data. And the other use case that we propose is an event venue, because an event venue is highly variability, the amount of people there, but in a short time. Is predictable because you have a calendar, but how the people move in that moment is not predictable and is dependent of other many things. So we think that both use cases are a good option to test the model. And also something very important is that when you apply a tool like an urban digital twin, you want to solve something, you want to solve a problem. So select the main cases when that problem is arrived. Because if you solve the problem in these cases, your system will be able to solve problems easier, or problems in other cases that are not extreme like this. So for this, we propose to validate the model in these options. Then the outcomes, that is the most relevant part of our project. We have some system level outcomes. This is that we effectively made the data processing. We follow the data mining process, a complete data mining process. We was able to create the model table, which is composed by heterogeneous data. We developed a well-performing model. We miss the different data sets in urban data. This is a well-explained methodology. I hope we explain this in the best way. And we develop an API tool, and we develop software codes for each state. So we are talking about people the best way is the best way to explain something if with a graphical and usable tool. So we developed this API when you can upload your data, your basic data, and then the is more slow than I am talking. So you can upload your data, and the API will check that the data have the requirements, and then mix it, your data with socio-demographic information and land use information. You can download these results, as you can see, or you can run the model in the API. So it's running. The model is slowly always it's running. Yeah. And you get the results from the model using your own data. This is very relevant to mention that your data, you only need your GPS data from the space that you want to evaluate. So there you have the predictions, and you can download your predictions and go to the other page in the API. Use your predictions for the visualization part. Analyze your predictions in a graphical part. By default, the predictions that are outloaded are the prediction from our data. And that is, you can select a specific district, you can select the specific census tract, and you can select the different days that you want to graph the data. So this graph is the real value and the predicted value for that data. And in the table, you can see the error for each value. It's a comparison table for the results. Passion. And you can see the result for different days at the same time. And you can on or out of, the one day, or make whatever you want. And also the area is plotted, and the characteristic variables are printed in the API. Then also you can select your own results and see what happens. If your results have some problem, you will see an error, because your table have something bad or are not matching with the requirements of the data. But if you have the correct format for your table, you will see that your data will be uploaded, and you will be able to analyze your own results in the same way with the graph. You can select the area, the specific area, and like that. And everything you can do everything that I already explained. This is very important that at the moment, the data that we have is for the Madrid district. But for example, if you want to analyze Paris, so we need the land use information from Paris and the social demographic information from Paris and that. But you only have to provide the GPS data that you want to analyze. This is because our model is thinking to be usable for the users. So the more relevant is that the users can use this in a simple way. Read a script is not simple, it's not funny, it's not easy to understand. This way is better. So this is our API. And for the conclusions.
So the one question is that what value our model will add to the existing practices. The first one is because our model is trying to integrate the heterogeneous data, the static and dynamic data, to build a model table that can explain the spatial and temporal pattern of the population, the movement of the population. And also our model is adaptable, and we try to generalize our models, whether it can be worked on another species, like molecular interchange, and also the stadium and the urban park also. And of course, it definitely provide the human data layer into the urban digital twin for informed decision making. So also there is a lot of there is a scope of improvement to make our model more comprehensive. One of the key things that we can integrate the mobile network data. In our thesis, we have mentioned how we can integrate the mobile network data, because mobile network data is provided at the district level. It's a cursor level, but we can from the model from our model we can predict the population at the center census tract level by using the GPS app data. Then we can use those GPS app data to calculate the spatial weight, the proportion of the number of unique app users from each census tract. That from that weight we can disaggregate the mobile network data. We can disaggregate the data from the district level to the census tract level. So we also try to describe how we can integrate, and that will be definitely that will add another dimensions in our model. And we can also add different data layer, because we are selecting 1 week data because of the hardware constraint, and but we can use the largest data set. We can include the weather events, also some disruptive events like strikes or normal or natural hazards. We can consider the traffic congestion data into our model. So it's a adaptable model. So we can also integrate those those data into our model to make it better. So before finishing this, I'm again thanking you, Natalia and Pablo, for their outstanding support and guidance. So thank you, Pablo and Natalia, and thank you, everybody.
Yeah, it's working. Thank you very much, Ali and Asha, for your presentation. And now I give the microphone to the jury. Who wants to shoot the first question? Okay.
Okay, so thank you very much for your presentation. As I expected, it is an impressive work, and it is quite a piece of art. I have a couple of questions, because I think this work deals with a lot of data, and I would like how to try to get into a company and how to get profit from it. So for doing that, I think it will be interesting to know if you have guessed what will be the cost that you have of your work during this Capstone project. So think about your development as an asset of a company. So what might have been the investment, the invest amount of money, and how could you get profit from it? Have you thought about that?
Yeah.
Okay, so let us know.
Okay, Ash is the businessman, so he will tell you about money, about that aspect related with the technical part. For example, you need us, because if you want that your urban digital twin really works in the real world, you need the information about the people, because an urban digital twin is nothing if it doesn't know what is the people that will be the users for that application. So this is why. related with how much. For example, in this case, the data, Pablo can tell us about what is the cost to get the GPS data, and the other data sets like sociodemographic information and land use information and cadastral information are open data sets from the public organizations. So tell about
Yeah, the first one, we also try to, especially in the middle of our Capstone project, to try to analyze the business value of our model. Basically, we got the data from Normon free. So according to the current situation, our benefit cost ratio is infinitive. So, but definitely the GPS app data is not for free. This is the crucial things that we need to know, the cost of the GPS data, but it definitely, because many companies are selling their apps, selling their data. On and though we in our mid level in the mid time of our Capstone project, with that we try to evaluate that our model can the business benefit cost ratio can be more than 2, but it is still I think it's reasonable, because any benefit cost ratio is more than 1 is viable, but it is even is double of the cost. So the profit is almost double. So that's it.
Yeah, we think that the most expensive part will be in the computational resources that you need for to develop the model and train and testing
Because
the
I
model.
guess that you run that on in your own computer. You didn't get
No, we able to use a virtual machine in the UPN server that have a lot of computational resource like 64 RAM or something like that. So
And also
it was free for us, just for us.
and also, for example, we are basically dealing with 1 week data, but when we also try to just plotting the GPS app data for 1 month, so still our laptop could not handle this. So we have an access to UCL, the University College of London. I have got access from there, so to plot one month data.
Okay. That because you just has answered the second question I was going to make you, that what is the time horizon that you have been working with? Because last year we had a capstone that was dealing with what was the impact of high population events like the ones you mentioned in the mobility inside a city, inside a territory. Apart from that, I think, have you tried, well, you were saying that you have captured the expectation of population just taking 1 week, but have you shifted that week through the year? I mean, have you tried to use data from 1 week, maybe in January and maybe in July? Because in Madrid, the traffic population the traffic and the population change a lot during winter and during summer. So maybe that's all. So did you check that it worked pretty well as well in January than in July, for instance?
Yeah, actually, for to select the week, we analyze the weather conditions in the complete year, the calendar, because the mobility changes a lot. Is holidays, if it's summer or something like that, because the people is around the transportation or not, or we analyze like different factors, calendar, weather, special holidays.
We have found that the May and October is quite normal if we consider, because in the summer season there is a lot of tourists is coming in the Madrid, so we did not consider. So we try to identify the normal month, whether everything seems normal, the academic calendars, the mobility, the commercial, the businesses. So we found that the May and October is the standard month. So from that we use the October data.
Okay. Okay. Thank you very much.
Like that previously in order to to train the model with the more typical condition, typical patterns
Okay.
in the data.
Okay, so you got future work to develop in that area. Okay, yes, I will give a space.
Thank you.
You too, Alex.
Uh, Yes. So I also wonder if you restricted your data to 1 hour or 2 hours, I don't know, during the day or
No, we have 24 register for each day. What we did for was like hour interval for 1, 2, and then to obtain the 24 register for the complete day.
okay. And so when you do the correlation analysis that you showed with the square, did you do that for a specific hour of a specific day in the week, or did you consider the correlation over the whole week and all hours?
Yeah, the general correlation for the whole week.
Okay, because it seems that the correlation would change quite a lot depending if you are, let's say, during the work hours, there would be strong correlation with the land use of work, whereas if you are in the evening, most likely more correlated with the housing, etc. So maybe it would be good to have a dynamic correlation analysis depending on the time of the day or something.
Yeah, very interesting. If I couldn't, I will write that in the improvement in the future research. I will add that part because it's very interesting. Thank you so much.
And so can you say a bit more about what you would do with more resources using time series analysis? Because as Alex said, then you might be able to predict the future evolution for the next week if you have data for the current week. So have you already thought about that? What kind of models you would use or stuff like that?
Yeah, that is also in the future research of our improvement, because if you be able to work with a larger horizon, time horizon, you will be able to identify cyclical or temporal patterns, and with that huge volume of information, this better to resolve this problem that like a time series problem, and you will be able to use more expertise or better models like LMTS or transformers or that a lot of crazy models.
Okay, and maybe one last question. So if we think about way ahead in the future, like a few years or 10 years, I don't know, and imagine that there's all this data coming from the mobile phones and you have a much better resolution at the level of a building or and a much better time resolution. Did you think about ethical issues regarding privacy, etc.? So have you thought about that?
Our model can predict the population movement at the census tract level. This is our highest resolution. But it's possible if you have because it depends on the resolution of the GPS update also, and the building information from, for example, we also thought about because from the satellite image analysis we can identify the height of the buildings. Standard we can from the height of the buildings we can also identify what types of building it is the residential or the commercial. So then we can build a relation between the height of the building and the uses of the building with the number of the number of the population. So even we can disaggregate census tract data into one more final level. That's the building level is possible. Our model, that's why we're considering it is adaptable, because it's very flexible. We can inject and we can also go deeper if we consider the building level also. Yeah.
Okay, thank you.
Thank you.
I only had one question. What's the limiting factor for scaling your prediction quality at this point?
What is
The limiting factor, that's it. That is mm, uh, uh, for you to be able to scale your prediction quality.
The number of the target variables.
So, how would you be able to scale? Would you keep the same model? Would you adapt to a different one if you want to cover a broader geographical area, or if you would want to have a larger data set? How would you be able to keep the prediction quality high and scale this as much as you can?
I think the the best way is to maintain the quality of the data that you are using. This is the GPS data, the basis of the analyze. Um, Also, it's really important that the socio-demography and land use information be updated, because sometimes your GPS data is from, I don't know, last year, but your land information is from 10 years ago, so you will have problem with that. So the best relevant part is to maintain the quality, the most updatable data that you can, for maintain the best performance of the model in different scenarios and different geographical cases.
But the model can predict, as we have mentioned, that from this, as we can predict the population movement at the census tract level. So it's easy. We can also predict the population at the district level also from the aggregation, by the aggregation of the number of unique app users. We can also predict the population at the district level or even beyond that.
Maybe a last quick question, Christophe?
Thank you very much. Yeah, I don't want to ask too many questions regarding the data set, but as a final thought for this, have you considered any kind of similar type of data usage? What are not especially people, but you can apply the same idea. For example, wildlife or anything where when the object of the analysis is moving, but maybe you have a little bit of less variables and less factors. What might cause any kind of distraction in the movement?
At this moment, basically, we are only thinking about the GPS and mobile network data, and with some other, as usual, the static data. But one potential data source could be what should I say, the transport of the ticketing, the ticketing information, because ticketing information, and that means when we move, so definitely the transport authority have the information about the ticketing. So from that data, we can also predict the movement, but not for we can analyze the pattern of the movement also.
A good idea is to use external data for validate the GPS data. But if you want to use the basic information from other source that is not related with geographical information, it could be, for example, the ticketing, because from the event venues or transport station, the assets is saving. So you know how many people live there or how many people out of that place. Wi-Fi, Bluetooth, particular systems that capture the number of people moving in a place. It can also be value for this kind of application. So I think it depends on what do you want to know what do you have for that, for to get that information. You have to adapt the model to use one format, or to locate the users, or another. I don't know if we reply your.
Yeah, you have answered the question. It's just so you only thought about very similar data. So I think that based on your whole global idea, we could use it for very alternative reasons as well, to analyze certain patterns. And with the whole system, just with different kind of data. In that case, you were focusing on this and where it could be applied directly. Okay. Then I will give.
Thank you. Thank you for your questions. Thanks again,
Thank
Ellie,
you.
Ash. We can congratulate again.
Finally.
Yeah. Sorry again for the sharing of the slides. We're gonna, yes, we can have maybe a little pictures with the title, and you can have a little picture as a souvenir in front of the. Yeah, you can.
We want to invite Natalia and Pablo.
Of course.
Take the picture with us.
Meanwhile, if you want to have a few minutes break before the next capstone, feel free to go to bathroom or have a coffee, or I will call you like in 5. Let's say we start at 15.
Because you have the light before you. Yeah. Yeah, because you have the light a little bit left. Yeah, again. Voilà. Perfect.
¿Me tomas una luz mi móvil? ¿Qué tal?
Bien, está bien. Buena. Ah, vale,
Yeah, with digital a little to the left. Yes. Just yes, because
because of the
I'm sorry.
maybe behind
It's tricky. Yes. On a black.
Mario, ¿me tomas una minta?
pero si quieres te la ayudo.
Yes. Digital twin. Okay.
I am an academic. It's not recommendation of PhD. It's not about what is. As you want. It's only like. People are watching you online. You're welcome. Congratulations. So people online, are you still with us? I think.
Yes.
Perfect. We
Yes,
can hear you.
yes.
So if you want to say a few words, you can also everyone is hearing you in the lecture hall. show a presentation. Yeah, you have to give it to me. Correct. Or you put it on a USB key. Correct. Yeah. I will give it to you tomorrow morning. Is okay? Don't spend the whole night in the slide. No. No, we already have it ready. Okay. I just didn't brought my laptop. No, it's easier if it's like PPT, classic PPT. Yeah, I will put it on a key and. Thank you. I'm copying past. I mean, I copy the PPT on my laptop locally to be sure that it will be fine. If you want to just look at it to be sure that it's everything is fine, you can. So everything is fine.
Yes.
Okay. Yeah, perfect. Okay.
Yes.
It's okay. It's a good version. Perfect. Okay, so let's click on let's wait a second. Simple. Is it yours or is it your dance? Your dance? So don't forget. Here. C'est vrai. En fait, c'est les templates. Peut-être que c'est à la fin aussi. C'est vrai, ouais. Je pense qu'en fait, il y a eu ce template et. Ouais, il n'y a pas de. Bon, yes, I got it on my laptop locally. I copied it. Yeah. Well, we have the logo here. Alors, let me just. Here, Zoom. No, it's not Zoom. I don't want Zoom. I want that. And that, I think we can put it here. Okay, so you can, Jan, you can use the mouse or the keyboard and the arrows if you want to for the slides. We don't have like a pointer. We don't have a slider. It's up to you as you want. Do some room here. What? I mean, the sooner we start, the sooner you are finished. You have a battery for the microphone. But if you want to move a little, you can use this one and you put it close to your mouth. You can stick it to your chin. Yeah. Okay. Well. Very little people.
I think that's this framework is no longer in there. Also this title. So. I don't know if we can edit it now, but the introduction and objectives that I do.
Check this.
Mhm.
Start with introduction. That's okay.
Mhm.
And be the active. You can present the objectives. If you later, I can go pages and bridge monitoring and development. Explain. That's okay.
Yes. I'll grab my phone too.
No.
Just on the schedule. Okay, so everything is shared.
Hello again. If you can take a seat, please. We're going to start again. And people online, you can still hear us. Yes, say yes if you can. Hello?
Yes.
Yeah, perfect. Thank you. Perfect. So we're going to start with the second capstone with Jordan and Alenka and the partner company CH. So Peter, if you can just introduce the collaboration between your company and BME. Thank you.
Hello, guys. The way you know me, I'm Peter Kology from Tech. Yes, Peter Kology from Tech. I'm the head of bridge design at Tech. We were the industrial host for this topic. And I'm very glad of my students and all of you that you completed this course. Obviously, I saw during these months my colleague Gabor in the office putting a very huge effort into this topic and this work, and I'm glad you fulfilled and completed. Course Tech is very enthusiastic about digital twins. We are now learning and trying to explore the ways where to go, where to move in the future, and I hope sooner we will find the optimization way and optimization phase, and then of course at the end we can make money of this knowledge. So thank you all and congratulations. Good luck.
Okay, thank you. Thank you to Peter and to all of the participants and administrators of this program. So here we're going to present our capstone work, which is a digital twin of the Gubachi Road Railway Bridge. A little bit contents. We are going to start with an introduction, objectives. The framework is bad contents, but it's not our in the current presentation. But we'll describe a little bit about the methodology, how we create it. We'll stress a bit on the sensors and basically ways to collect data in our digital twin. We move on to the actual development and we draw at the end some conclusions, challenges, and potential improvements. So starting with the introduction, a little bit of context. In Europe, Europe has the most extensive railway network in globally. We have over 2,000 kilometers of tracks. A lot more bridges. I was surprised by the statistics, but one of the issues that are very common in Europe is that most of the infrastructure was built after the Second World War, and 75% of the steel bridges are older than 50 years. A need for digital twins in infrastructure is one of the goals is to capture the whole lifespan of bridges and enhance maintenance and monitoring. So we had some not difficult, but tragic events that led to a failure of infrastructure that has a very high socio-economical and has very high socio-economical impact. Sorry. So about the bridge, although this bridge is not not an old bridge. Still, the development in this capstone can be used to, can be extended to old bridges. This is a new bridge. It's located in Hungarian part, Hungarian railway, part of line 1 of the railway network. It is part of an enhancement program of the Southern Link that of Budapest that aims to increase the capacity of the railway. Oh, I'm moving. So about the bridge itself, it's a 54-meter span. It is a war and truss steel bridge. It carries single track, ballasted. It's part of a very complex urban junction between railway. There is a tram line underneath and railway. So okay, so our task is to create a structural digital twin, and we start with defining what is a structural digital twin. There is a quote by George Box that essentially all the models we try to model, all the models are wrong, but some are useful. This is a quote from statistics, but can be applied also to infrastructure. In every model we create of the subjects that we're trying to develop, there is some sort of error or misalignment with reality. So a digital twin is a good tool to capture reality, put it back in the, not back, but put it in the digital world, and use the data that is collected to enhance operation and maintenance of those structures. So yeah, here, since the bridge is not built, we have to simulate a real bridge. Okay, so why a digital twin? Regular maintenance is quite crucial for infrastructure, for infrastructure to well, to live long and a lot of collapses are related, bridge collapses are related to improper monitoring and improper maintenance of bridges. So objectives.
Hello. So now I'm gonna talk about the main objectives and then the technical objectives that were developed for our digital twin. So for the main objectives, we have the development of our digital twin network. So first we created a mind map and then a specific framework for the different steps. Then we have the selection of technology for the data simulation for the sensors that we chose, and also for the management, storage, and exchange of data. Then we have the use of the bridge weight in motion system, and that is to determine the axle weight of the railway cars, both passenger and freight. Then we have the bridge response reconstruction that's based on the data that we export from the FEM model. And then we have the development of the structural data visualization in the system that we chose, which is Tandem. So then the technical objectives were creation of the high fidelity FEM model that we used ANSYS. Then we have the modification of the digital twin framework that was to suit our objectives for the definition of our structural digital twin. Then we used Technostructures, which was the IFC model that was provided by Tech. and we included a mapping between BIM and FEM and how to export that data then for visualization.
Okay, so about the methodology, basically this is the entire workflow of the digital twin. We start with exporting the IFC model to get geometrical dimensions of our models. Then we model everything in ANSYS. From ANSYS, the aim is to extract the simulated influence lines of axle moving across the bridge. Then we had to generate some train loads based on reality. From this simulation, we get a time history, strain time history, simulated sensors, and from there we can infer axle loads from the way in motion, and we can assess the fatigue lifetime of some details. From that point, we have to track the state of the structure, and we have to showcase what is the current state and what action should be taken in order the structure operators and the maintenance team to work on the bridge. So from this point, we should be able to update the BIM or the bridge information model and run the loop all over again. Project phases are setup and modeling. What the main milestone is to have a FEM model and BIM model suitable for our use case. Then we have to assimilate data and surrogate modeling while not implemented in the current development. It's very helpful to create a big data set for training for the models that operate. So the data assimilation is also a part where we input all the collected data into the digital models and create the first flow of information from physical to digital. And yeah, then we have the probabilistic graph model, which is actually this model tracks the digital state and infers the digital state of the structure based on the measurements we have from the real world. Then we have to integrate everything together. So it's actually done in closed network with APIs for communication between the components. At the end, the last phase is visualization of the results and testing and test deployment. So, about bridge monitoring.
So for our bridge, we considered many sensors from strain gauges, accelerometers, and like temperature sensors and whole environmental sets of sensors. But we ended up choosing the strain gauges for our digital twin because not only they were cost effective, but also easy to deploy, and the data collection would be more easy to implement to export our data and then to connect with the rest of the variables. Yes. And then for the bridgeway in motion technologies, this is a way to provide a way to obtain the a vehicle's weight while it remains in motion. So this bridgeway in motion uses sensor signals that are generated by an instrumented bridge to determine the axle weights and the gross weights of a traveling vehicle. In this case, it would be a train instead of a truck, and different sets of trains, which are 2 and 3 axles. And then we have the Bayesian bridge weights in motion, which is this method integrates the uncertainty of our estimation directly into our axle loads and weight determination process.
So for technologies for AFM modeling, we chose ANSYS because of its APDL extension, which is basically a scripting language. We can control many of the geometrical and analysis parameters, not many, but all of them, just from scripts. The Tekla structures is for opening and manipulating the bridge information model that we have available. For data or machine learning, numerous Python libraries. The computing infrastructure, it's a normal workstation, nothing particular. We chose some databases like timescale DB for time series, sensor or response data, and Neo4j, which is database for storing graph database. We chose Docker for containerization and Tandem for the visualization part. Well, yeah, here is the justification of the technologies we chose and overview of already the development. So we aim to create a virtual representation of the bridge. We need to, not we need to, but we chose to adapt the framework in this paper. We need to be able to enable the bridgeway motion and to store data in the digital twin. And we, for phased build, which is in phases. So the architecture of the digital twin, it's a standard architecture with data acquisition layer, middleware, and application layer. And basically this is the workflow. So now the creation of the FM model. The first important part was the geometry and loading. I have created some supporting Python libraries to help me with the complex geometry you can see on the right. From FEM, we extract the influence lines for the locations of the sensors. This is done by running multiple analyses and collecting results for a single point that represents the sensor location. After we have acquired the influence lines, we then move to the train simulator. So we have to somehow simulate a passing train between the passing train over the bridge. So we try to base our simulation on reality measures. For example, we have chosen the parameters taken out from reality, like information for trains, for compositions, and we also developed a load distribution between the axles that is somehow near the reality. With the simulated train and already composed train, we can then, using the the influence lines, we then obtain simulated signal of the sensors. This is done by running the train loads over the influence line, and we then get a very clean signal, which is not possible in reality. So we corrupt the signal with some noise. Then we have to apply the Bayesian bridge Wayne motion. The reason why we choose a probabilistic method is that for proper maintenance and monitoring of structures, we have many uncertainties because we can measure the structure only at one point. So we have to find a way to propagate and to first quantify and then propagate all of the uncertainties and include them in the digital models. This Wayne motion, probabilistic Wayne motion algorithm is basically the same as the original Wayne motion system, but instead of optimizing the difference between the measured response and the theoretical response, it just optimizes the. I'm sorry, I missed that, but it quantifies the uncertainties and the correlations between the measurements and the theoretical. Basically, it makes it probabilistic. So the algorithm is the following. We input the time series. We pre-process the time series. There are two distinct sensors that move the calculation of speed and axle distance of the between the axles. That it's basically divides the inference of bridge parameters. One sensor array is dedicated only to the weighing of the axles, and another sensor array is dedicated for vehicle parameters like speed, axle spacing, and so on. So we build the observation vector, and we do a prior. We set the prior means of the parameters we want to extract, and then we update and compute the parameters we want. This calculation is then inserted in a probabilistic graph model, which basically updates the different states at the top of the graph. Those are different states of the structure that on the second part we observe the structure. Then from this observation we decide the digital state of the structure, and then we move to decide an action and actually record the action that we have taken. And at the end, we have a reward system that penalizes bad decisions to keep them in the model. So, yeah. At the end, this is transferred to the visualization part.
So for our visualization and integration of data, we use Autodesk Tandem, which is a software that is for digital twins. So what we did first was to simultaneously introduce our IFC model into Tandem and then establish all the data connection points that were correlating in the geometry of our FEM model. So for all of we used 6 sensors, which were set in the middle of the bridge, where we have the most stress in our model. So all of these sensors were then set to time and strain parameters and categorized into the families that we have in the tandem templates. Then for each of these connections, this one missing? No. Okay. So so then for each of these connections, we introduced strain time lapse through Postman. In Postman, we use it as a gateway to introduce our CSV data, which are measured in time and strain parameters. Here we introduce our data through JSON scripts, and the data is then posted to each of the API links for each of the sensors in the model. So then that information is posted and we can visualize it in the digital model. Next. So, for example, this is one of the links for one of the API ends. This is a simplified CSV file. Most of our, this is an amplified result CSV that we input into the system just to be able to visualize in a higher amplitude what our results are in the system. For each of these connections, then we run the analysis, and once that is done, that information is posted into Tandem. Then this information is updated each time. When we have connected into Tandem, we are running the information live, but that information needs to be updated using an API key for each of the connections. And then for interactive data visualization, we can select the sensor that we are wanting to measure. See which ones are live and which ones are not. So then each of the parameters also has a threshold where we connect the streams, and that information, for example, that you see in red, we have that threshold simulated to a point where it would indicate that we need to do like an action, issues an alert where we are over that threshold of values. So then this information gives us it gives us the data that we need to intervene where we do the analysis for fatigue cycles. So then from the digital model, we can then infer into what we said earlier about how to connect that into the physical assets to provide a structure operator and the maintenance team with this information, and then provide what action would need to be done. And then from that, we can continue to do our updates into our model. And we would have a new updated set of values, and with that done control action that would be inputted then again into our bridge FEM for continuous updates. Should I continue?
Yeah.
Okay. Okay, so then for our conclusions, we see we have a potential value for this tool for structural health monitoring because it aids us for our maintenance decisions throughout the lifespan of the bridge. It also provides a dynamic and integrated platform that we can simulate and visualize and then assess the structural condition of the bridge in each of the sensor positions, which would then be scaled into different parts of the bridge. So then by enabling this early detection of damages, we can provide a very an elongated lifespan for a bridge and try to prevent failures in the future. So this architecture of data would also allow us to integrate, when the bridge is built, real sensor data and also scale it to incorporate different sensors, which would provide us with a better overall like description of the bridge for physical, for a digital model.
Okay. For the limitations and challenges, we have a lot. The one are technical. It's high fidelity FEM models are very demanding. Sensor data fusion is quite hard when we have different sampling rates. The model validation is always required. We need to be sure that the models are within certain ranges. There is one challenge that for infrastructure monitoring, a lot of big and extensive data sets are virtually non-existent. So we have to either create them or simulate them. There is also the cybersecurity challenges that most of the systems we have envisioned and we have studied, they focus only on the digital twin part, the modeling part, the digital models part, but they don't consider any cybersecurity. And this could be an issue because we want to, at one point, we want to have a real-time monitoring. And if improper cybersecurity can delay transfer of data. There are no platforms for digital twins for infrastructure, mainly because a lot of different digital models are in place. And yeah, there is also from data point one big limitation is that there is no common data scheme. For potential improvements, it could be better if we can include machine learning integration, mostly in the structural assessment part, the simulation part, where a lot of physics-informed machine learning is being developed. That means that we encode the physical equations that govern the behavior of the structure. We encode them in neural networks and advanced AI. So this would be very beneficial for creating large data sets or running simulations on the fly, basically, and real-time assessment of and reconstruction around of the entire response of the structures. Yeah, predictive maintenance also has a place to be, also has potential to be improved by artificial modeling with artificial intelligence. When decisions are made on a structure, AI can help a lot. Another improvement, modeling techniques need to be adapted for different for the differences of the structures that we see in construction. Basically, every structure is unique and faces unique conditions and challenges. So, automated modeling from, for example, from BIM towards FEM is will be a very big improvement because we can actually update very fast the FEM models. And then improvements are the data fusion of sensor combinations. Those are sensors that measure structural response and track also the environmental conditions, and also, yeah. And that was us. Thanks again for Tech and their availability. Thanks for Attila, and thank you for your attention.
It's working, yes. Thank you, Jordan and Alenka. But now it's time for the questions. So who wants to start? Yeah, Jeremy.
Thank you for the presentation. So I'm not sure to have understood if you can go back to the last slide where you have your overall framework. Yes. So you mentioned at some point the paper that you worked with from Torzoni, I guess.
Yeah.
And this mentioned pins, finite element, reduced order model. So did you implement that or? Okay.
It was, we were constrained by time, and at the end, we just converted to influence lines, and this was, otherwise the idea was to create some sort of physics-informed neural network that will assimilate sensor measurements into the FEM model, basically, and provide the model updating techniques that we need. Because if we want to track the structural state of a structure, we have to update also the numerical models that represent it, the digital model that represent the structure. This was intended, but was not implemented.
Okay. And when you mentioned the probabilistic analysis based on graphs, I'm not sure what kind of uncertainty you try to account for. Is it the uncertainty from the measurements or other types of?
The measurements and the inferred, like the calculated axle weights of the trains. The idea was to calculate to have a weigh in motion system and to reconstruct. I think I've missed the slide, but to reconstruct the stress time history of a certain detail and to examine its fatigue lifetime. And to do this, we cannot use deterministic values because everything is it's changing. So the idea was to put into this framework to input also the measurements suitable for probabilistic graphs. I mean, the weigh in motion system, if it outputs just the calculated weight, we cannot then perform probabilistic fatigue analysis, and from this point on, we cannot. We have to be deterministic of how long the structure will wait, so will sustain loads, and this is problematic in structural monitoring because we can underestimate the lifetime or overestimate the lifetime in the condition.
Mm.
So we always have to propagate that, okay, we are measuring something, but we are within this tolerance. And yeah,
Okay,
that's the main reason to inject wave motion data with certain with uncertainty and correlation into this framework.
And here, did you do any fatigue analysis?
This slide, I'm sorry. Basically, the fatigue was done with rainfall cycling, cycle counting, and we just append the normal distribution of the axial weights. We append them to the cycle counting. We have not reconstructed distant parts of the structure response. We used the placement of the sensors where we place the sensors. We use this for stress time history. But
so what was the estimated lifetime of this bridge?
It couldn't be, we didn't actually do it and validate it. Okay. It was just an intention, and we described this on a theoretical basis, but without implementation.
Okay, and maybe last question about the beam FEM mapping. I don't know if you did some work on that or you just took an original FEM model that was existing, or you did create it maybe?
We created the FEM model by measuring the BIM model.
Mm-hmm. But you did everything by hand. I mean, no automated process.
No. The automated process includes ontology. Basically, we have to parse the entire IFC. We then have to say, in simple words, we have to say, well, this is this element from the structure from the the BIM model needs to be mapped to this type of FEM finite element, and those properties have to be taken from this part and attached to the FEM model. So to the finite element. There are developments, but they are not implemented.
And then you have always issues of parts which are not connected in the BIM model, and you have to connect them in the FEM. So I was wondering if there was some new technology to fix this.
Basically, the FEM model was one of the biggest parts of the development, and it was manually created. So, but a big area for improvement is actually automated one, even with the input of experts that map FEM BIM objects to FEM elements.
Okay, thank you.
Okay, then I will continue. I understand you had many challenges along this way to get here. Well, you also presented at the end quite a long list of risk and issues. Based on what you have learned during the process, what do you think could be done a bit differently, and what could be a good conclusion for anyone who's starting a similar structural digital twin? Because there are many things what could be a similar issue. If you don't have data about how your structure is, what happens with your structure when it's damaged, then it's the same for any similar structural digital twin.
What could be done differently? The collection of the digital models. Basically, simulation can be done very well, provided we have proper digital models. And most of the conditions that a structure lives in and operates in, they also can be simulated. And with the help of machine learning techniques, this could be improved. The process has to be holistic, however, because structures have very long lifespan. We have phases. So one is design and planning and design. Then we have construction, the actual construction, and then we have operation and maintenance. Even though this twin was done with models found in the design phase, it's better to have them from the construction phase, and even better if they are created when the structure is commissioned. So this is one different way. I think it would have been better to start with the models that we have from everything and to measure from real world structure instead of trying to simulate what could happen. You have something?
No.
Yeah. Okay.
Thank you.
Okay, so congratulations. I know that you had some difficulties to reach this point, so I think you made a great effort to reach this presentation. So I would like you to congratulate you on that. I was wondering how many sensors are placed in the real structure?
In the real bridge, you mean?
Yeah.
There are currently no sensors that are going to be placed in the real bridge, but we place them within our stress points from our EFEM model.
So I was wondering that one of the problems that you might be facing is that the ones related with the storage data, as you said, and the cost related with that. You are wondering about the fatigue life is going to take a long time. So you are registering a lot of data. So what would you think that it could be a wise way to save storage space? So by selecting, or how could you compress all the data that you gather in terms of strains or deflections?
I think those strain points could be denoted when we have like the real bridge, and we can update our geometrical models, and then from the loads that we have, we can assess those stress points and then place the sensors there, and then from there provide approximations to other places instead of placing sensors every like every 2 meters or something.
If I can summarize, we first is to optimize the sensor placement, to have as little sensors as possible. And this leads to the second part where we were using numerical methods and physics-informed machine learning. We can reconstruct the entire response of the structure based on a small amount of measurement. So the goal is to decrease the points that we measure and to increase the capabilities of the digital models to reconstruct everything from one or two or small amount of points. Other than that, it's a good idea is to have a windowed measurement, for example, to detect where a train is passing, because in civil structures there is a lot of environment
Conditions,
input, from supports from the environment, and this windowed method will compress only to the frame where a train passes. A good thing for railway infrastructure is that trains are scheduled. They are not random as vehicles on the road. They are within fixed routes.
So synchronizing the moment that when you are getting data.
Yeah.
And the schedule of the trains, I guess.
No, but we have to detect anyway the axle of the entering train, because it's a peak in the sensor signal. So this data frame can be slotted, but
well, you can set a trigger on that sensor. So when it surpasses a certain level, it starts recording.
And analyzing and storing the data. We can always receive the data, and we can operate on the data in real time. But when we pass this threshold, we can start recording and analyzing everything.
And another thing that I was wondering is, which part of this project do you think it could be transferable to other bridges? Because it's for sure the calculation of the fatigue life, it will depend on the age of the bridge, geometry, materials, etc. But do you think that some part of your development could be transferred to any other bridge? Because that may be a way to saving costs.
From the things that I worked on the most, the train loads generator. This is something that can be based on reality, and even from manufacturer of trains or carriages and locomotives, we can get the exact data. That's another good part from railway, that everything is set on. There are not many variables in vehicles. This is one of the developments, and the way in motion is also transferable once we obtain the influence lines, and the lifetime assessment module. Basically, when there are modules, each one of them, we can transfer them to other structures with modifications, of course. The idea was to have something developed in a network that is with components that communicate within each other. So every component is interchangeable with advanced or simpler one, and they can communicate with each other. That was one of the.
Okay, thank you very much.
Thank you.
Questions from my part?
I don't have any question, but I think what you showed us today here is basically an argument for open source and open data. Because if you would have had access to I mean, it seems it took a lot of work in order to provide like a good PEM model on which you were able to do your work, and having that as a prior condition and accessible to many entities, that would have saved and would have been, I think, a better approach. But yeah, that's all that I wanted to say. That I like the presentation a lot.
Thank you.
Okay, thank you. Thanks again, Jordan and Lenka.
That's it.
Yeah, that's it. Congratulations. What time? I think it's time. So we can have you can have a picture if you want to.
Yeah, sure.
With Peter, by the way. And Attila, I think, is here also. Yeah, Peter.
Peter, Matteo.
And after that, we will have the break for lunch. You want to put a nice picture?
Of the
last one. I mean, maybe the last slide with all the faces. Oh, this one. As you want.
This one? We will be on the faces.
Yeah, you will be the faces.
Background. That was good.
One with.
Okay, thank you. We are going to have the lunch break, and we will be back at 2 p.m. First for the afternoon session, starting with Ineko and Adif Capstone. People online wish to see you again this afternoon. So have a nice lunch, and we'll be back at 2 p.m. Thank you.
Alors, le problème, ça va être de... alors, je ne connais pas du tout ici, il n'y a personne, mais la question que je vous posais, c'est pour recharger les micros. Parce que cet après-midi, ils ne vont pas tenir sinon. Tu sais comment ça fonctionne, toi? En fait, ça, ils sont d'ici, les micros. Donc, c'est de la salle d'ici. Et je ne sais pas du tout and I can be here beside. Of course, you can stay here. Where is Geraldine? Hello. Can you hear me? Laura?
Yes.
Ah, Mario, yes. It's not Laura. Let's just stay here. Let me just. You can say hello to Mario. Ah! Sorry. Where are you? Yeah. Now everyone can see you.
Hello.
How are you?
I'm good. Sad to
Good?
not be there, but I'm good.
Yeah, we all miss you.
I know, I miss you too, guys.
Ah, thank you. I was waiting for the microphone. So I can, yeah. So sorry, but I have to hide your face. So we start. Let me check. Yeah, we start with Ineco, then Arab and ISA. So I just need to prepare Ineco. Yeah, perfect. Let me just. We can. I can put. We can keep Mario here. And is it working? Okay. Take one.
Yeah, welcome again. Let's start this second session with the first capstone going by Ineco and Adif. And I will let Marcos introduce the project and the partner. Thank you.
Hello, good afternoon, everyone. I'm very glad to present this project, this capstone, in which Adif and Ineco have worked. Both Adif and Ineco have been in the top companies in Spain regarding digitalization since many years ago, even when the BIM implementation was starting. So now they are with us here also and helping us in this digital twins project. So I'm very glad to present this, and I want to thank Javier, Jorge, and Francisco Javier for everything, and Carlos too. So now it's the time for the students, so I'll let them present their project.
Hi, good afternoon to everyone. Today we are going to present our capstone project with title Malaga Maria Zambrano High-Speed Rail Station, realized by Mario Castro, Anshin Moria Comenan, and Federico Gulisano, with the participation of Ineco, Adif, and UPM. So this is the main outline of the presentation. We will start with a brief introduction about the topic. We will talk about the state of the art, and then a presentation of the railway station. Then we will talk about the inputs that we received from the company, which permitted us to define the main objective of the project. You will see that the project is mainly divided into three different parts: data processing part, machine learning models, and data integration. And finally, we will present the conclusion and future development. So let's start with the introduction. We have made a literature review about the use of digital twin for management of building environment. And we have observed that there is a huge potential of using a digital twin solution in different aspects. For example, for energy performance management, indoor environmental monitoring, space management, and hazard monitoring. While virtual design and construction technology, like for example BIM technologies, can be used for the design and construction. Digital twin solution can serve more for operation and maintenance. But these two kind of technology can also be integrated in what we call BIM-based digital twin solution. And for this integration, we will need some software, some integration platform for connecting the data with the BIM model. From the analysis of the state of the art, we have seen that some projects have been realizing these topics, mainly using a BIM-based digital model for university libraries and other kind of building. And the main objective is always to connect some sensor data with the BIM model and to perform some visualization and analysis of the phenomenon. But in the topic of railway station, we have observed lack of information about the BIM-based digital twin application. But we thought that there is a huge potential for employing digital twin solution for the development of smart station. For example, for station operation, like train schedule and traffic management, passenger services, and station management.
Okay, so now we're going to talk about the Malaga station itself. Malaga is a city in south Spain. It's one of the most touristic ones in the whole country. And the station is located right in the city center, very close to the beach, very close to all the tourist amenities. Next, Federico. Thank you. The station dates back to 1860, when the original Malaga-Córdoba railway line was inaugurated. The picture top right is the original railway station. Between 2004 and 2007, it went through a major overhaul to accommodate the new high-speed rails that were built in Spain, and Malaga was one of the first cities to receive the high-speed Spanish railway. In 2024, it received almost 9 million passengers, almost 2.6 million more than the previous years, and it has been a trend that it has been growing and growing and growing year after year. It comes with 12 platforms and 11 tracks, of which 5 are standard gauge and 6 are Iberian gauge. It comes with direct high-speed lines with Madrid and Barcelona, and medium distance to Seville, Córdoba, and Granada as well. Not only has high speed and rail, but it also has cercanías commuter lines and direct metro interface and of course, surface intermodality with other means of transport. Next, please. The station itself is a different concept to what we're used to, at least in Spain. It's called Vialia. Vialia is a concept created by Adif. Currently, there are 5 stations in Spain like this, in which bigger stations are not only train stations, but under the same building, there are different facilities, use cases, and of course, operators. In this case, we have 5 different uses of the same building. On green, we have the main rail station. On orange, we have a Barcelona hotel. On pink, we have a commercial area that is full of supermarkets, supermarket shops, and so on. It's basically a mall, a regular mall. You go inside and you don't realize that you're in a train station. And then we have the connections with cercanías in blue and with metro in yellow on the right. Next, please. Okay, now we're going to talk about the inputs that we've received. The first one, and one of the most important ones dating back to February of this year, was the meeting with the facility management team. We traveled to Malaga to meet with the real operators and the real users of the station to understand the problematics to understand the problematics that the facility has day after day. One of the main problems that they raised to us and that they were seeking some kind of technological consultancy from us was a problem that they had with the pumping systems that we've talked in the past about it, in which they basically take measurements manually of all the pumping system that they gather from all the building that we saw. They have 5 different operators, and all that sewage pumping is stored into, or is received by one common piping system, and all the measurements are made manually every 10 days. Next, Federico, please. Okay, so here is a table that we received with all the measurements that they have. As we can see, it's a measure every 10 days. And the problem that it has is that if there's a problem, if there's a leak, if there's something between those 10 days that we cannot control because this is not digitalized and this is not automated, it can occur that a div will have to pay a huge amount of money either to the city, either to electricity bills, and so on. We decided not to pursue this use case because from a digital twin point of view, having manual measurements every 10 days was a big lack of information for us. Next. Okay, next input that we received is the BIM models. The BIM models were developed by CITD and MSI, two Spanish companies, of course, in conjunction with ADIF and INECO. And they gather the three areas the areas that we see here on the right. The main station, the commercial area, urbanization surrounding it, the old buildings at the entrance of the station, and the cercanías platforms. Out of 40 models that were developed, next, Federico, please. We have been working with 23 of them. These 23 models are split in architecture, structures, and MEP, and more or less have a level of detail of 300, 350, most of them. There are some of them that are 200, in which the locations of the elements are approximate, but the models are very, very advanced. Next, please. This is an image of the BIM models that we are working on. And here we can see how advanced, especially the MEP systems are. We have structures on the bottom, MEP on the center, and on top we have the architecture models. These models have been developed under a DIF's database and a DIF BIM's requirements, which means that they are hugely advanced in parameters. Not that we have used them in this case, but it makes them extremely heavy, and it has been a challenge to process all this information in the platforms. Yeah. Next.
Okay, so after saying that, in the second part, we receive data from the company INECO, and we can say that the data is a structured data that is presented by a DOM file, MySQL. In this database, each sensor type, group, and information are well stored, and all readings are stored with units and thresholds. As you can see, the entity relationships of the database, the table type of sensor defines the type of parameters like semantics, units, and thresholds. The second table, group of sensor, organizes sensor into groups under a shared type. The third tables of the database called sensor lists the individual device that produce measurements. And the last one is the value that saw the actual time series of readings linked to each sensor. So we can say that regarding that database, this architecture presents a strong base for feed our digital twin platform. When we try to gather all the sensors regarding the type of data, we could say that regarding the ecological footprint equality, we have 16 sensors, like temperature, NO2 sensor, humidity sensor, PM2.5 sensor also. We have also sensor of crowd, people quantity sensor. We have also a sensor that helps to determine the intelligence management of the last kilometer. Because we have many sensors, we try to build a network configuration of all the sensors. It's the cartography of all the sensors in the station of Malaga. So regarding the different type of sensor, we was able to work on many fields of digital twin. So we were focused on digital twin regarding the monitoring of environmental parameters. So the sensor of that kind of digital twin are located on the platform 8. the suburban platform and the office block 4. And as you can see on the platform 8, we have all kinds of sensors regarding the ecological footprint air quality. So we decide together to focus and to develop a digital twin regarding the platform 8. Here you can see the cartography of the different sensors.
So from the input that we received from the company and the state of the art, we finally define our main objective for the project, which is to develop a beam-based digital twin system for environmental variable monitoring of the Maria Zambrano railway station in Malaga, with minimal inversion and economic pressure. So we are going to see how the work has been divided into a first step data processing, in which the data from the database are taken are getting cleaned and filtered. And then the cleaned data are used for from one side for the development of machine learning prediction model of two critical air quality parameters. And then also for the integration of this sensor data with the BIM platform.
Okay, so after presenting the architecture and the objective of the project, the first following step is the data processing. During that step, we try to build a pipeline to be able to go from the MySQL database to a real data set that can be used to feed the platform called USB IoT, the platform that we use to build our digital twin, and the data set ready for machine learning model. Regarding that, along the way, we use some validation criteria, like a sanity check, to based on the time coverage, the duplicate and unit consistency, to measure the reliability of the sensor that we use to build our digital twin. As you can see on the slide, this is all the pipeline that we follow to have the real data set, to feed the digital twin. Firstly, we read the data set, and after reading, we use the table the table sensor to enrich the data reading to localize them and prepare them to be cleaned. To be cleaned. After that step, we try to measure the reliability of each sensor to see if we are able to use this sensor or not. After that step, we try to apply some filtering function on the data set. And also because we have different sensors, we have also data that has captured with in different timestamp. So we think that it would be great if we have one timestamp for each data of all the sensors. For all the sensors, so we use some statistic criteria to find the best frequency to resample the data of the sensor. After we was able to provide a clean data to feed the platform and to use that to build the machine learning models. So let's get in depth. Okay, so regarding the data, we had some problem regarding the data. Why? Because as you can see on the tables, out of 4 million total records, we have only 1 million values. So it is really important to measure the reliability of each sensor. Also, the data, we can say that the data was measured between the between the year 2021, but the available data was after 2023. So we have data that was captured but not available in the database. In this slide, you can see the different you can see the time series of two sensors, humidity and temperature, and all the distribution of all the sensors that we will use for the platform 8. Okay, so to measure the reliability of the sensor, we use different metrics. We use gap detection, coverage, drift per hour, and recency lag. For doing that, we make an abstraction. We determine the minimum frequency between for each sensor between two measures to be able to determine the frequency of each sensor. And that assumption helps us to apply all the metrics on the data set, on the raw data set. Okay, what is the result of that step? We can say that all the sensors have poor quality data, except the CO2 that is moderate. And we ask the question if we continue or we stop the project, but we want to continue the project because we want to do some things. So we try. Okay, now let's apply the filtering function on the dataset. So to apply the filtering function, we have to be we have to not create data leakage because we want to develop machine learning models. That data leakage appears when you look the future, when you look the past, the present, and the future to clean the data. So you merge the future and the past, and that things creates a default to the machine learning models, and he could predict. He could predict, for example, values with 10% of precision, and it is not correct. It's merge the future and the past. Okay, so for that we apply the buffery causal filter. We custom that filter function with a cutoff selection, and we read on the literature that for all the sensors we have, this is the filter parameters that we have to use. And we apply the function, we filter the noise, but what if we lose the stationarity, or we lose the tendency of the trend of the data of the sensor? So to be able to assess that element, we use a stationarity test. If after applying the filtering function we lose the trend, we readapt the parameter of the filtering function, and we try to regain the trend of the data. And after, if it is good, we are ready for modeling. So we can see on the right some example of filtering. Okay. So after filtering data, we have now different data. We have now different timestamp for each sensor. But we want to have a data set that look like that. One timestamp for each sensor. So because of that, for doing that, we have currently different frequencies. Different frequencies. For doing that, we can, for example, resample the, downsample the data or upsample the data. So what is the best, what is the best approach to doing that? So I try to use different metrics based on, apply on the longest block without gap of the data set. The first metrics that I use, it's the coverage percent. The second, it's the alignment percent. And after after computing the two metrics, I compute the score with that function to determine if the frequency that I want to resample of my data is good or not. And in order to find the best frequency, I apply that function on a set of frequencies. I choose 3 minutes, 6 minutes, 9 minutes, 13 minutes, and 60 minutes. And the best, the global target was 30 minutes with an average score of 77%. So this is what we did to have a real data set for machine learning models and not ready to feed the digital twin platform.
Okay, let's follow with the machine learning models. This is our main modeling approach. So finally, we had a lot of environmental sensor from the station, and some of them are more related with the air quality of the station, while like the PM10, the nitrogen dioxide, and other kind of sensor are related with the environmental comfort of the building, like the temperature and the humidity. So from all the sensor, we decided to analyze the PM10 and NO2. I mean, to develop machine learning models capable of predicting the values of the concentration of these two parameters by using as input the data from the other sensor. So we decided to use this sensor because are considered the most critical indicators for public health monitoring, because they can cause high concentration, can cause respiratory problems, cardiovascular diseases, and reduce lung function. So for the models, we had a total of about 28,000 sensor data, and we split it into 80% into the training data and 20% for the test set. And we employ a random forest model. We decided to develop two different kind of models. The first one, which we call instantaneous prediction model, use current sensor readings for predicting the values of PM10 and NO2. But this kind of model can be used, for example, for interpreting the physical phenomenon. While we want also to develop some forecasting model that use sensor data from 2 hours before to predict the future of the concentration of the critical indicators. So we started from a feature engineering analysis, meaning transforming the cleaned data into data that can be used for the machine learning model. We realized the linear correlation analysis, in which we observed that some positive correlation between the PM10 and NO2, mostly with temperature, but also a linear correlation with other parameters. And the coefficient correlation are not so high, but we have to consider that this is a linear model. So we were confident that the application of random forest can capture some non-linearity inside the data. So then also another step was to use not just the value, the variable from the sensor, but also temporal variables. But these temporal variables, like the hour or the day of week or months, have present a specific challenge because they have a cyclical pattern where the end and the beginning values are naturally connected. For example, for the hour, 0 and 23 are naturally connected, but cannot be used in this way in the model. So we apply a cyclical encoding, transforming each temporal variables into two different variables, the sine and the cosine. For the development of the model, we need to perform a hyperparameter tunings of the models. Random forests are like a set of decision tree algorithms. So the main parameter that we can tune are the number of estimator, which are the number of decision tree that we vary between 50 to 200, and the maximum depth of the random forest of each decision tree. For this, we employ a cross-validation technique, which consists of using the train data and dividing the train data into different folds. So in each step of the process, we use one fold for the validation and the other folds for the training. And in the second step, we change the fold that we used for the validation. In this way, each data are used for the validation and the training set. And this can generalize more the model. This analysis serves to identify the best hyperparameter for each of the two critical factors. Like, for example, in the case of the PM10 model, we found that the best hyperparameter were a number estimator of 200 and a maximum depth of 20. And we didn't want to extend too much for a computational reason. So these are the performance of the model for both parameters in the train and the test set. In this graph, we can see the actual value of the sensor and the predicted one. So we can observe that we obtain a very high performance of the model. But we also have to consider that this model uses as input variable for example, the reading sensor at specific instant. And here we can see the trend, for example, for one specific day of the actual concentration of the parameter and the predicted one. And we also perform a sharp analysis for interpreting the result of the machine learning model, which permits us to identify the impact of each input variable into the output. So we can see that mostly the temperature have a positive impact in the concentration. So tend to increase both PM10 and NO2. But we actually wanted to realize some forecasting model. So the forecasting model are designed to answer the following question. Given current environmental sensor readings, what will be the PM10 and NO2 in 2 hours? So we repeat the analysis with data from 2 hours before, and we obtain the result that we can see in the graph in the right. We can see that in this case, the performance are a little bit lower. We can observe a higher dispersion because we are using data 2 hours before. But still, we obtain good results. And we repeated also the performance evaluation for this specific day. And for the sharp analysis, we can see that basically the temperature and humidity have the most important impact on the two critical parameters. So we think that this kind of application can be useful for the management of the station.
Okay, lastly, we're going to talk about data integration, how all this integrates into the digital twin solution. As we were saying, we have tried to create a digital twin with information that it's already there and with minimal economic impact and development. In that approach, we didn't want to, or we thought about building our own platform for storing the digital twin, but we thought that using a commercial software would be a better solution since we want to prove a point. It's easy, it's fast, it can be done. For doing so, we partner with Aka Software. Aka, for those who don't know, it is an Italian software company, very well known and very renowned for many years into the BIM software, at least in Europe. And the last creation that they had was USB IoT. It's a plugin that connects BIM with IoT integration with using the Beam cloud that I already have. It allows real-time data streaming, as well as historical data management. It allows us to create custom alerts and thresholds. And one of the best features that it has is that it has cross-platform access. We can access this digital twin from any screen that we can imagine, since everything is cloud-based. It's important to mention that it works with OpenBean standards. So we are not going to be working here with Revit models, but with IFC in our case. Next, Federico. Thank you. So this is a rough architecture of our solution. First, as we've mentioned, we start with the Adif database. Due to security constraints, Ineco's team created a data dump with part of that whole database from previous projects that we've mentioned. And with that data dump, we imported into our own MySQL that became the original project database. From that point, we arrive into Python, we do filtering and cleaning, and we split two different ways. On one way, machine learning models, and another way, we export a CSV with the filtered and clean data. That filtered and clean data is fed into Node-RED. Node-RED is a coding language that uses nodes instead of text. And that is the one that USB IoT platform works with. On the other hand, we started with the Beam models in Revit format. We had to export all of them into IFC in order to upload them into the USB IoT cloud and be able to connect them with the sensors. Next, Federico. Okay, so how does Node-RED work as a middleware in this case for the USB IoT cloud? As we see here, it's very similar to Dynamo for those used to work with Autodesk environment. Basically, it's a function, it's a code that we create, but instead of using text, as I was saying, we use different nodes. In this case, next, Federico, please. The first thing that we do is read the CSV file. The first node, the big one, the long one that we have on top with all the route or with the path to the file, that one creates a JavaScript object with all the information contained in the CSV. So the CSV node that we have highlighted here, what it does is converts that JavaScript object into JSON. Okay. It creates one object per payload and one payload per timestamp, which is equivalent per row in the CSV. That means that we are going to have all the sensors under one same JSON schema. This is not useful since we have to feed every single sensor into the platform individually, but we'll see how now. Please go on. One of the problems that we have with this solution is that it feeds all the data at the same time. It reads everything, processes everything. So we had to include some kind of simulation to recreate that frequency of one message every 3 minutes. As we see on the left, the payloads are sent directly, all of them at the same time. On the right, we see how they are split in intervals of 3 minutes. This allows us to recreate the real-time sensoring, even though our data comes from measurements in the past. The next one is a function, a JavaScript function that allows us to transform all the data into what into what into what USB IoT requires, and to connect the data that we have with the different data points. Now, next, Federico. Thank you. What are data points? Data points are basically the virtual sensors inside the USB IoT platform. In USB IoT platform, we have what is called technical plan systems. It's basically the equivalent of the digital twin or the data of the storage of the digital twin data for our project. Basically, it contains an array of sensors that are the data points. Next, please. Here we have all the data points or virtual sensors that we have created and we have used in our project. All this data is coming directly or is being fed directly from Node-RED, and as we see here in the status, that is the actual value that the sensor has in the last moment. That is the last fed value into the platform. Next, for identifying these different data points, we have, or the platform provides us a GUID, a unique identifier that we have to feed into the payload in order for the platform to know which metric goes to which data point. Next. So that being said, what does this function do? First, it splits the timestamp into 7 different objects. One object per each sensor, its data point that we have. Next. Secondly, it includes the GUID as a header in the payload. That way, whenever we feed this payload into the platform automatically recognizes each one of the measurements as, hey, this is temperature, it has to go to the temperature data point. This is humidity, it has to go to the humidity data point. Next. Lastly, it replaces the current timestamp with the original one coming from the CSV. We wanted to keep the information of the original measurements, of the original data into the platform. So instead of using the timestamp of when this node is processed, we are using the timestamp of the original measurements. Next. And lastly, we have the WebSocket itself. The connection in this case is made via WebSocket, something similar to what an IPA could be, but reversed. Please go on. So the connection is made via URI to that URI that we have there. In yellow is highlighted the project ID. The same way that we have the GUIDs for the data points, we have a project ID that identifies our ID inside the cloud uniquely. So whenever we feed the data into that system, into that URI, we have a problem. How do we know that we are the only ones able to send data into that? How do we know that no one is able to access that data? How do we know that that data is protected? So the platform works with mutual TLS authentication. Next, please. Basically, we receive 3 different files from Maca software certifying the connection. An X509 certificate with its public key, a private key for this certificate, and a certificate agency file verifying the procedence of the certificates in order to verify that we didn't fabricate those certificates and that ACA software is a trustworthy source for certificates. Please go on. So this is an example of how it works in real time. Node-RED works in a local server. Once we hit timestamp, that it will be equivalent to a start, we see how on the right it appears the first payload. And here in the limit node, we have 27,700 rows of information sent at the same time. However, on the right, we only see 1 row of information, 1 payload. That is what the limit message does. So here we see how in Node-RED, the first payload is processed, the values of all the GUIDs, timestamps, and measurements for the first instant. And if we go into the platform, here we go into technical plan systems, we go to our sensors, and we say here how the status has been updated with that last measurement that we have sent into the platform. As we see on the right, the last update, that date is 2023. That is what we meant with it. If we moved to the viewer basically, we have connected the sensors to a beam element, in this case, the sign of the platform 8. Here we have the last values with their units seen in a very easy way, but we also have different dashboards that we can create and customize. These dashboards are basically Grafana. The platform works with InfluxDB and Grafana in the background. It's not something that we manage or we have any control over it. ACA software does. However, if we want to ask them different tweaks or changes in the configuration, they can do it for us, as they have done. That value in red we're going to see now. Next, Federico, please. So this is the perfect example of the thresholds and rules that we were talking before. Here on the left, we see how, or the beam element in which we assign the sensor. We don't really know the actual location of the sensors in the station due to security problems with the previous project that took all the measurements and all the sensorization of the station. So we assume that everything was in the sign of the platform 8 inside the beam model. Here on the right, the 425 value is what I was mentioning, the threshold. We can set rules and thresholds inside the platform. It allows us to do that, and we can see we can see the alerts in two different ways. One, the dashboard will turn red, or whichever color we configure. In this case, was red. We can see very clearly here that the CEO is over the limits over the acceptable limits that we set up into the platform, and it's giving us an alert. In this case, it's a dashboard, but we can also configure alerts in means of notifications. That's it.
Okay, so to conclude, we can say that we built a beam-based digital twin that supports ESG impact. For the future development, we try to build a MVP digital twin platform that use open source software like Grafana, API, REST API, and CO kits, Beam Viewer, and so on. So thank you.
Yeah, thank you. Thanks for the presentation. Now it's time for the Q&A session. So who wants to start?
Thank you all. Thank you for your presentation. I want to congratulate you for your work, first of all. I think you did a lot of things. You know, I like these ideas a lot. So, and I know your efforts are limited, and the time, of course, probably would lead to many things. I think you've used all the technology that we teach in the master. So in terms of education, I think it's a very nice project. But now I'm interested in your opinion in some issues, okay? So you think you say you go for a beam-based digital twin solution? Well, it made me think a lot when you said we need smart stations. And I said to myself, aren't they smart already? So the problem is that maybe now we have a lot of brains and you want to integrate it. All of those brains in one, and maybe beam and digital twins, beam-based digital twins can help us. So then you focus on machine learning, and then it was a relief for me that I saw that you did a platform. So after this presentation, I was wondering how important do you think is Beam for this type of solution if you focus only on one use case as the one you chose?
Maybe I can start, and then my colleagues can follow. And yes, I think that in my opinion, what we try to develop is just like a starting point for a more complete digital twin solution, and in particular a beam-based digital twin solution. Also, you mentioned, for example, the machine learning model. I think that in future could be integrated into the beam model. This is something that we miss. We perform the analysis in different step. Maybe one next step will be the integration of the models, the machine learning model that we develop into the beam model for a better visualization and management of the station.
Yeah, if I can add something. Okay. So, in my opinion, I agree that maybe beam models in a solution like this that is, let's say, a simple solution are virtually useless. They don't apport much information into the solution. However, we consider, at least personally, I consider them a first step. It's true that for a solution like this, they don't put too much value into the equation. But if we think on the future developments, they can give us many different solutions for a bigger, let's say, digital twin. I'm imagining different simulations that we can do once we have more data, for example, no, without BIM models, or not BIM models, but 3D models, we cannot create any kind of simulation, or very hardly we can. One of our initial ideas was focusing on the passenger, for example, and one of those ideas was trying to create a digital twin that allows us to manage the spaces into the station, since it's a commercial area, right? For creating, let's say, simulations. Okay, what if we put a stand or shop here in this plaza, in this lobby, for example? How would the flow of the passengers would be affected? So those kind of solutions that are a bigger spectrum of the digital twin that we have created, of course, is very far from what we've created, but once we start gathering data, as we've seen, there's a lot of data in that station that is being gathered, or that was gathered. So the BIM model apports a lot of value into those new solutions. That is true that are far from the one that we have developed.
Okay, thank you. I think it's quite clear, and well, that's one of the things I was wondering. That probably I understand that this is an academic project, so but probably I always say in these projects that you choose the most profitable use case as the first one. So I was wondering if train stations were unhealthy or were highly polluted or something. And probably, of course, you had the time you had and the data when you had it. But if you started the game and you saw the platform already done, what use case do you think would be the most profitable to develop?
Yes, I think that one of the, as you said, we had a different option, different use cases, and finally for this project, we selected the one that we were interested on, but also was the most viable. So we had some other idea. I think one of the main idea that we had was to integrate also the passenger flow data, and maybe to do some not just prediction model, but also to actuate in real time in the station using, for example, in some part of the station, changing the temperature of the humidity based on the flow of the passenger. Maybe can be some interesting solution. And then also I think something about the management of the traffic of the rail. But we actually thought a lot about the passenger topic, but actually we didn't have time to continue.
Okay, thank you. Just to finish, because I believe the rest want to ask something. When you develop a use case, think that it can also serve for other purposes. For example, in this case, you could use the gas measurements to predict the lifespan of the concrete structures or some other issues that can make the return of investment much faster. Okay. Congratulations and thank you for your answers.
Thank you.
Thank you. So I had a question on the machine learning model. So you mentioned the forecasting part and the instantaneous part. And this one, I don't know what's the purpose of that, since I guess you have the data now at a given time.
Okay. So yes, basically we had data. We had data, an amount of 28,000 data about this kind of sensor with each timestamp. So the first idea for us was to develop, to predict the value, for example, of PM10 by using the temperature, the humidity, and other type of sensor at that instant. So this was what we call instantaneous prediction model. But actually, we also thought that if you want to manage the station, maybe we will need some forecasting model. We want to predict in advance what will be the concentration of the PM10. So in this case, we change a little bit the database, the dataset, in order to get as input parameter the data 2 hours before. So this was the main.
Yeah, so the forecasting model, I really see its usefulness, but I don't see in which situation would be interesting to have only instantaneous prediction, since, or maybe it's the case if one of the sensor fails or something. Or...
Yes, for us it was. I think it is useful for interpreting the phenomenon, to understand what are the main important factors that can affect actually the concentration of these two critical parameters. So it's maybe it doesn't have application for real-time monitoring for sure, but for interpretation we think that can be useful.
It's more related to a correlation analysis or something. Okay, understand better now. And maybe another question. So you mentioned the pumping issue at the very beginning. So what would you propose to maybe solve this issue or improve how things are done, and to have better maintenance of the pumping system? Or do you have some
Mario, do you want to answer?
Yeah, reply. The problem basically that we had with that use case is that the measurements were done manually. So every week we would receive a new Excel file, or every 10 days. So it was too time consuming for the time that we had. It wasn't feasible for this project. The solution is, at least on my point of view, it's simple. A digital counter that sends measurements directly. The problem is that those exist already, but what they told us during the visit is that apparently the company that installed them is not the company that managed let's say, the cloud in which those measurements go. They had a fight, literal words of the station management team. They had a fight between the two companies, and they stopped getting the data from one another. So the station ended up being with the only solution that they could, that it was taking the measurements manually. The solution is simple. The hardware is there, so it will be a mean of getting back in contact with the companies that installed all the hardware, and putting the solution back on track. And with that, we will have real-time data that we could use for anything that we can imagine.
Okay, thank you. So it's interesting to see that technical solutions almost always exist, and that the problems are sometimes coming from other issues, more
exactly,
human issues, etc. Thank you.
Thanks. Is there any more questions? Okay, thank you very much. Little picture as a souvenir.
With Mario.
Yeah, of course. Let me
screen,
drag
please.
Mario. Let me drag Mario. Can I don't know if I can. Oh, yes. Maybe we can. Yeah, of course, of course. That's I can't. I think it's the maximum size. Yes.
better like that.
Yeah. You can be on top of them. Yeah, we can't put him on the on the left side. Huh? Thanks again. So we can have like maybe 5 minutes break if you want to go to bathroom before the next capstone. Thank you.
I was going to ask. Is it the last one?
This is the last one.
From. Yeah, I can put
okay.
it on my computer now if you want.
Okay.
It will be like, I prefer to do it now. We have 5 minutes.
Thank you so much.
You're welcome.
Actually, from the questions, we got some stuff that has to be added.
Okay. I will put it on the desktop.
Great. Thank you.
Let me just check that it works. Perfect. No. I wanted to remove. Let me give you back your USB key. I come. Where is my? It works. You're welcome.
Can I do 1 minute thing to open a couple of pages up?
Oh yeah, of course, yeah. I mean, I think I don't know if I mixed. What was it? I think it was this one.
Yes, and I have another one which I can.
Up. No, you have to select it. Or just click with that. Yeah. I think it's fine. Yeah, you have to.
Yes.
There are two tabs. Yeah, the top of it you have to.
I cannot see the mouse though.
A little you can open it, no problem.
I just want to alt tab it quickly before we do anything, right? Now.
And yeah, perfect.
Close the review because it was not.
If you click on.
It was not important.
I have no clue how to make the screen mirror.
You prefer to
mirror? We don't need to know.
Yeah, we don't know. Here is some notes, but we don't
I think it's this one here.
Duplicate?
I think it's this one. No, it's not
and
that.
If you do alt tab right now on the presentation itself.
No, it's not. It's not that. Sorry, that I did. Yeah. It's not. It wasn't that. No. What did I do?
It's okay.
Yeah, yeah.
Yeah,
You
you
don't
have
wanna
to.
be,
Yeah, but I made a little mistake here. I shouldn't have. Yeah. So
It is not. It's copy down below here.
I think there is a way to.
No, I
No,
know.
no, 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 no. No one is going to see the.
They are not also even important.
So what do they see here? No feminine. Wait, it's weird because I don't understand. Yeah, I think I broke something because it's. I don't understand why.
Would it help to
What
close
is?
it down and open it back
Yeah,
up again?
I guess because I don't understand. Yeah, let me close it and start again. So we are still sharing the screen, yes. Okay.
We change your format.
No,
I
it's-
didn't like the color.
Yeah, I saw that.
Tuesday's blue.
I think what we can do is.
We can leave it like that.
Yeah, yeah, yeah.
Yeah,
It's fine.
I know, like.
You know, just move maybe
Yeah,
this one here.
yeah, exactly. That was I was looking for. Okay, let's talk everyone.
Don't worry. Don't worry, we got.
Oh, we're starting. You know, waiting. He just went to okay, they did it all. The last group.
Like you haven't heard.
No, I'm just afraid. My voice start to shaking, and if it's going this way, I cannot stop myself. You should continue.
No, it's okay. Keep going. Let's say bring a bottle of water.
I don't. It was not there.
You want a glass? We can share mine.
Yeah, it's fine. It's fine. No, just take it. Danny, you can sit. Yeah. Because it's long. It's 40 minutes at least takes. Mario, are you here? He's not here.
Mario
Just left.
is probably gonna have a beer right now.
They are not interested in our project. Coming.
I can just turn on the microphone and be sure that everyone is. Yeah. It's fine. It's a sound not blocked. Just to be sure that.
Yeah, it's the bar slot.
Mm. I think.
Are we still? I don't see the control.
Whatever. Okay. Yeah, audio. Okay, everything is working. Okay, perfect.
Okay.
Okay, so let's continue because this afternoon is quite busy. So let's go ahead with this other capstone that has been proposed and supervised. We stood on the help of ARUP and the Barcelona Supercomputing Center. And it's also a great honor because it's the first, I think, the first capstone project that is supervised from an alumni. So we are very happy for that. And apart from that, I give you the floor and good luck.
Thank you. Hello, everyone. Thank you to being there and listen to us. Our Capstone project is about urban digital. Sorry, I cannot use that one because I'm working with my hands a lot. Okay, our Capstone project is about urban digital twin for assessing and simulating safe route to a school in European city. My colleagues are Nikolai and Danny, and I am Negar. Okay, let's start to have a brief review of our content and what we are going to tell you. The first step is introduction. After that, we will tell a little bit about the state of the art, challenges and objective methodology, develop of digital twin in 2 case study, Barcelona and Bologna, result and analysis and conclusion. Okay, let's start with this step. Why this project for us was important and why we are looking to have a safe route to a school. I can say children's safety is one of the important problems that we have in urban designing. So as you can see, 1.35 million children are dying during the traveling to their school by traffic accident. So, and this number during in European is almost 430 each year. And the average that is happen, it's between 5 and 29 years people, and I can say between a student. And you see, it's we are in a dangerous and we are in a problem. But I can say this is not just related to the lives. Actually, with this problem, people and students, they lose their activity. Means they just more take by by parents and by public transportation or private car to their school. So they lose their activity. And in other side, we have some problem related to sustainability. So about existing safe route program that we have already, I can say they have helped actually almost 50% of this program that they are ongoing help to solving this problem for a student. But I can say they are not updated, and they have missing some information, and they are, I can say, they are not new. So for example, for some specific behavior of children that is related to the low income student, we have still some unsafe environment, or I can say some issue related to the disabled children was not solved with this program. So they are looking forward to having a new solution and a new idea by having urban digital twin in their system. So having this urban digital twin in the city can with using a dynamic information and using the data-driven parameter can give us better understanding and simulating of a safe route to a school. And you can predict the situation of a school and guess the future of the safe food for children. So this program, UDT, it's updating these days, and it's going to help a lot the cities and also the children to having safer and I can say a greener and sustainable way in the city. Let's look at overall about a state of the art and research that we had. The technology nowadays it's growing a lot. During our research, we understood this technology like AI, 5G, and even edge computing help a lot this saving route to having better result and having better monitoring in our city, and you can have a better prediction without building and having a better result before creating the safe food for a student. Among this research, I can say the problem is most of this I cannot say implementation. This project that are going, they are like a pilot project. They are not really a real digital twin implementation project in the city. But in some cases, like Helsinki, Rotterdam, Barcelona, we have a very good cases that more or less 22%, 20%, I don't know, even Barcelona, almost 40% can control this bad situation, this traffic situation, this accident situation around the school by having the system of AI or digital twin, improving this system in their city. The methodology that we understood they use in this kind of pilot project or these researches, we can divide it in 3 steps. That one was gathering the information or data from large scale mobility and traffic data and try to understand and clean this data and doing this simulation. And the other one, it's related to system to integrate this framework in just one twin with governance information with very specific data in just one small twin. And the way that they do the second way is a simulation and driving different kind of tests and predict the situation of the route. But still we have some gaps and problem that we will mention. So let's start with challenges and objectives that we will have during our research and what we want to do. Okay, challenges is we have some challenges, and front of these challenges, of course, we have some target to upgrade and improve this problem. The first one that we understood is related to safety and infrastructure. That the simple things is, okay, of course, you have to improve your infrastructure. The simple thing is you upgrade your sidewalk, your crossing, you create a calm zone, create a standard safety score for your system. So it is not difficult. The second one is related to technical barriers. These technical barriers, you can control it as we mentioned with real-time data integration. You can understand the algorithm, the routine algorithm for a specific behavior of the children compared with the adult very easily with this simulation, and even integrate IoT and also private data. But you should be careful about privacy of a student with children, and even how you can keep everything safe. And the third part, it will be about evaluation and long term. If you want to have evaluation and long term process for your digital system, of course you need a system that is a standard, and your indicators is include with a good base of construction. So you can monitor them, and even about the cost, you should have a right framework to understand what is it the situation, even relate to the cost of the city that you have in your project. And the last part is related to implementation, and the solution can be about having the flexible funding, and even you can have some a small project, the digital twin small project for the even a smaller large of cities, and involve your stockholder and even family with this project, and try to understand the situation of the project for them. Maybe with this communication, they can be more convinced to have to giving your fund or support your project. So the objective, we understood we can during this project having a different kind of objective, but we started with developing evaluation system. What we wanted from this developing evaluation system, it was creating a multi-criteria safety, that is a safety score coming from our data, like traffic data, school route, environmental, infrastructure, and social data, and a lot of other information that later we will mention most of them. And this can also work for decision support tools, means this simulation model can work for municipalities, can guide them, can help them. And in our case study, we chose in our project, we chose two case studies, Barcelona, because overall we had 10 cities, but between the 10 cities we decided to pick two important one. One was Barcelona, because we pick it as a general case study for implement our project and methodology, and it works like our I can say more scalable and flexible project and test bed. And Bologna, it's selected because it has very precise parameter and specific parameters. Then you can understand, okay, this system can work with most of the city in Europe. So it's very flexible and scalable. And the third part, we mentioned, we understand we can focus in addressing inequities. As I told you, we in our city for sure we have some vulnerable zone or weakness. So if the municipality or your city maker can understand this situation, okay, they can do fast reaction, and they can manage the situation better. And the technical objective that we will explain in our methodology, it was gathering data, giving a safety score, a routing simulation and integration, and creating some simulation about our safety route. And at the end, we ended up with application. So let's start with our methodology. The overall view about our methodology is we have two, as I told you, we have two case study. Barcelona is very scalable case study. It's very general with general information. It's test bed for our methodology, and Bologna is more local feature. It has more local feature parameters, and it's very precise. And this project, it's run in 4 phases of workflow. We started with identify parameter, developing a standard method, a routine algorithm, and simulation and testing. And we show that this model is very modular, because you can combine your universal basic parameter with your specific and city-driven parameter, and you have this ability to transfer this methodology to other city that we have, that as we did for even for Bologna, from Barcelona to Bologna. So you can see it's very flexible. So more in detail, our methodology, if I want to mention this for phase work for, started with identify parameter. What is it, this identify parameter? What we did, we tried to gathering our parameter, our data, and try to divide this parameter in different categories. For example, we had six categories, like geospatial data, sensor data, social and economic data, operational data, and each of these categories had their specific parameter that we call all of this chart as a basic parameter. Plus, we had some specific and city-driven local parameter, that this parameter, it was belong to each city. Means for Barcelona we have super block that is just belong to the Barcelona, or for Bologna, that later we will mention it, we had some specific parameter that it was, for example, for historical layout or ZTL zone, or public transportation, that is specifically it's related to Barcelona, to Bologna. So for us, this city-driven parameter for the second case study was very important. The second step, it was developing a standard. What we did, okay, we tried to clean our data, harmonize our data, giving a score to our indicator, and normalize all of our parameter that we have between 0 and 1 for compare our parameter. The second step is creating to routine algorithm and creating our networking and understand the situation of them. Our route in the city according to the safety and cost. And the last step, it was a simulation and testing, and at the end up with our apps. Okay.
Brilliant. Thank you very much. Can you hear me okay? Okay. So we started the Urban Digital Twin for Safe Routes to Scoot framework in Barcelona. You're probably wondering why, right? So Barcelona for us represented a very modular, transferable, and deployable, Barcelona for us represented a dense urban network with diverse school mobility. Therefore, it's the perfect candidate to build a modular, deployable, and evaluation system for safe routes to school. Inside of this project, one of our main objectives was to be able to create parameter-defined weight safety scoring system that we're going to use those parameters to be able to implement dynamic routes, pretty much try to calculate the safest route, the shortest route, and a hybrid path in between those two. Utilizing that data, we start analyzing and creating different persona-based profiles. For example, if a person would like to choose to travel to school, that would follow a more greenery path, we've implemented that. If we have a person that is more aware about pollution and he wants to travel through the lowest pollution values within the city, we also implemented that, and through the mobility and safety as well. The other modular, I would say the other module that we have implemented for us, which was very important, was the simulation of the environment. Like what types of micro intervention we can apply and what impact they would have for our safety. All of these functionalities, they have been encompassed into a web application for the exploration. As my colleague said before, we started this process in Barcelona by collecting the data and having a look at it. Cities, they usually define into two types of data. We have the base parameter data, which is more related to that information that all the cities should have, such as infrastructure, pollutant, accident records, I would say safety elements as well, and city-driven parameters, as you will see in Bologna. Within Barcelona, we focused more on the base parameter just to show that these types of information is just enough to create a model that can be able to evaluate the safetiness of a street and create those types of routes. Collecting these types of parameters was very difficult, and that was one of the main reasons we stuck in Barcelona with the base parameters. The city-driven parameters, they were very difficult to get a hands on and access the data. Therefore, we've utilized different, I would say, platforms to be able to collect the data. One of them is the Quick OSM through the QGIS, where we've collected information about infrastructure, such as street layouts, such as crossings, such as traffic signals, school location, bus stop. And the other one, which was very important to us, was Open Data Portal from Barcelona, where we were able to collect information about pollution agents and safety information, as you can see. The other thing which we tried to integrate was live data into the system. Even though this data is statical, we try to integrate and create modules to be able to integrate live data. And the two live data that we have, that they are accessed through APIs at the moment, are the traffic information, which is got from the TomTom, and the weather information for the city of Barcelona. All of this being imported into the system in real time. Now we're going to start with modeling of the physical system for Barcelona. As we said before, we tried to build something very modular and automated that raw data can get in, be processed on the fly, and present information. Therefore, to be able to build such a system, we've divided our framework into 4 different layers. The first one is the data layer, with pretty much we analyze the data and create it to be able to be visualized and imported into the next layer, which is the database layer. And the database layer would pretty much, we're going to be storing all the information and perform special operations on it. The third layer, it's the backend layer, which pretty much holds all the functionalities of the system. And the last one is the front-end layer, where all of this information can be consumed and the user can interact with the backend layer to be able to produce new results, right? Starting with the data layer. Inside of this layer, what we have done, we've pretty much prepared the raw data to be able to be visualized initially, so we can understand the geometry and the kind of data we were dealing with. The second step within this environment was data cleaning. A lot of the data sets, they came with null values, with, I would say, missing information. Therefore, we had to do a little bit of a data cleaning process, just filling all the information and validating that the data is correct. And the third step for us, it was data harmonization and vector and special operations. Within this step, pretty much what we've done, we've had a look at all the individual parameters and seen how we can integrate it from a safety point of view to our infrastructure data, which is pretty much with the street. So to be able to explain down there, what we have is 2 different data sets that we've performed a special operation within this environment. The first picture, it has all the accidents that happened in 2024 within Barcelona, but these are just a location of the accident, but nothing more to it. Therefore, we have to perform a special operations where we had to pretty much create a buffer around every street, intersect it with the accident, and figure out how many accidents actually happened on that street segment within 2024. What we try to achieve within this environment is pretty much prepare the data to be visualized, analyze the geometry, standardize the data, and pretty much unifying it through a common, I would say, coordinate, no, through a common coordinate reference system to be able, so we can work within it. Have in mind that all the vector and special operations we have done at this point, it was for us just to understand how the data would look like and to validate that these types of operational processes, they can actually be performed before they were automated, right? Moving on to the next, I would say, layer, which is the database layer. This was a very important layer because here we're storing the information securely and we're giving our framework the ability to be able to perform vector and special operations through the PostGIS extensions and creating the graph street segment that is going to be utilized to be able to create those streets, to be able to create the navigable route through the city, right? And this was achieved through the utilization of the PG routing extension of the PostgreSQL, where all the streets in Barcelona, they have been converted as edges, and all the nodes, they are represented by the intersection of all the street edges and their endpoints. Moving on. Now, this comes where it's very, very interesting, because this where we had the most fun out of it, is how the hell can we create a pretty much backend and a data pipeline that can communicate everything. So our initial thought within this environment was to create a pipeline that is able, first of all, the backend to communicate with the database, querying the data, send it back to the backend environment, perform operations, and then feed it back to the user. But at the same time, we wanted users' inputs as well. So what we've done, we've created a two-way communication where the user can visualize the data, can apply changes to it. The backend will request the information from the database, will perform the special operations and the evaluation functions, and will present it back as a result to the users. Within this environment, apart from the data pipeline that we need, we have performed a different number of functions. Here we've implemented 15 visualization functions just to be able to visualize through the front end all the raw data of the city. We've performed 17 evaluation functions where special operations together with, I would say, a normalization to be able to identify the safety of the score has been performed, and several routing functions. Now, going into every function, here we have the visualization functions. You can see pretty much this is the data from the information, and there we have the visualization functions. What happens here is pretty much the backend through the visualization function sends an SQL query to the database, ask it to give me the data for that particular parameter or that data set. The SQL sends it all the way back to the backend, and then the backend is just packs it, converts its geometry into an EPSG 4326 that the leaflet application later on in the front end can consume and represent, and packs it everything into a GeoJSON format to be able to provide a lightweight transfer of the data. Now we have the evaluation functions. These functions, what we tried to do here, it was pretty much responsible for retrieving, again, the data from the backend, perform the special operations at the database level, and apply a weight and apply pretty much an evaluation score to it. The way we've done it, here we have a lot of scoring functionalities, operations, which some of them they have been utilizing counting, for example, to be able to classify where the safety would lie in between that street. We have normalization, logarithmic normalization, weighted normalization, linear interpolation. Pretty much on that table, we have all the data set that we've utilized, and the combination of all the functions and with the description of what exactly we were expected to obtain. Here, we're just going to provide just two examples of a couple of functions and their operations, how they've been performed, because we cannot go through all the 17 of them. So on the top right-hand side, what we have, it's pretty much the speed safety score calculation. What we've done, we've created a buffer around every street of a 15 meter. Then we intersected the geometry of the speed camera with a street segment, and then we start counting how many speed cameras we have pretty much for that speed segment. And then we apply the classification function to calculate the safety level of the street based on the safety score of the speed camera. This is how we've done it for that one. For the 3 safety score calculation, this gets a little bit more interesting, because what we've done here, we've used the same buffers that we have created above, and then around every tree identified within Barcelona, we created another buffer. We started by intersecting these buffers and calculate a calculate the coverage ratio, how much of the tree canopy will actually occupy within our street segments. Based on that, after we've been able to calculate the coverage ratio, we've applied the normalization function to be able to calculate that number from a 0 to 1. 0 represents the lowest safety score and 1 the high safety score for every segment. And we've introduced a floor parameter that pretty much, that doesn't mean exactly that every street that doesn't have a tree is not necessarily unsafe from that point of view. So we've introduced capped parameters as well. Now into the routing scenario and simulation logics. These are our third type of functions. What we've done, which pretty much we're utilizing all the evaluation score that we've calculated previously within the evaluation functions, and we're going to allow the user in the first instance to be able to insert how important that data set from a safety point of view it is for him. Based on those numbers, our algorithm knows how important that data set is and applies it into a weighted function to calculate the final safety score for our street segments. Now, to be able to route based on those parameters, we have utilized the Dijkstra algorithm, where the Dijkstra algorithm, it utilizes the street network created within the database to traverse the system. And this algorithm performs that it likes, as it traverses, it likes to select the lowest score instead of the highest based on our safety system. So therefore, we have to set the cost to 1 minus our safety score to be able to allow the algorithm to create those paths that we wanted. The second types of routing functionality that we've developed inside of Barcelona was the shortest route within the system. And this is pretty much where the Dijkstra algorithm utilized just the raw value of the length of the segment within Barcelona. And utilizing that, it was able to create us the routing that we need. Now, what we've done here and why we've calculated the shortest path is to introduce a third functionality, which is called the hybrid scenario routing. What we're doing here, we're pretty much combining the safest and the shortest route into one single route, where the user can select the level of safety he wants and the level of how short the route should be. This is done again through the Dijkstra algorithm. Therefore, we've introduced the alpha parameter that was able to calculate that balance in between how short it would be and how safest it will be, where if alpha is equal to 1, therefore our algorithm is going to spit out the shortest route. If alpha is equal to 0, within our system is going to show us the safest route. And if alpha is equal to 0.50, what it's going to do is going to prioritize at the same level the safety and the shortest path to school. And the last one, the last types of functions that we have for the routing scenario, it's pretty much on the profiles that we mentioned in the beginning. As we mentioned, we have people that probably they don't really care that much, and it's not really great to say about safety, but they would prefer, they're not in a rush, they feel safe, but they would prefer to see greenery around them. So that's what we built. We've had pre-configured profiles with weighted inputted into them that would reflect that types of profile. And the way it's done it's pretty much the same as the first function, where it takes all the safety scores, it applies the safety evaluation through a weighted function, and it calculates the route. And as you can see in the picture, I think that picture is for the greenest path. The blue line, I'm not sure how visible it is. It actually shows that that route, it actually prioritized the streets with more trees, and that they are trying to be way closer to the parks as well. Now, coming back to the intervention simulation. What we wanted was to be able to simulate how intervention within the city can affect the safety scores and can affect our city. What we've done here, the way we've approached this, it was by introduction of a sandbox environment within our system. When a scenario on, it's applied through the front end, what it happens, it creates a session. Therefore, our code automatically knows, don't run all of your simulation through your database. However, create virtual tables that you can perform those simulations in, where you can calculate those scores that you wanted. The reason why we've done this, it was because we wanted for the user to be able to add infrastructure, delete it, or update several parameters without messing up with the initial system, right? Because all of the functionalities, they've been built in such a way that they are automated and they work with raw parameter data. Within this mode, the user, without doing anything, you can perform all the functionalities presented before. And if the user is happy with the changes he's done through his simulation, he has a commit change button, which pretty much packages all the changes and sends it to the database for the model itself to update. The last layer in this Barcelona development for safe routes to school routes, it was the front layer pretty much. And this is just a very nice representation on how the application works within this system. As you can see on the top, you have like all the show school, show crossings. Those are represented by our visualization functions. If you press that button, all the raw data from from the database would be represented through the front end. In the evaluation, part, we have all the safety scores per individual parameters that they are calculated in real time. The customized route priorities, that allows the user to be able to set the importance of their weights for the user when they would prefer to calculate a route. And there, all the way down the bottom, it's the personas and the routings. I'll show the video at the end. We need to hurry up.
Okay, let's start with the second case study that it's Bologna. As I told you, we picked the Barcelona as a bigger, more general and test for our methodology, and Bologna for more precise and focus in local parameter that we have. For example, if I want to mention about the specific parameter that we have in Bologna is related to the 62-kilometer portici. This portici is arcade that people can walk through the city. As you can see in the picture, you can see some example for this portici that really control the traffic of the city, even in the center of Bologna. And we have a zone about medieval street network and ZTL restriction in Bologna that it makes sense we chose Bologna as a second case study to test our methodology in a more precise way. So the goal was to understand, to gain safety evaluation of a school route for this city. And the output, it will be 6 times a scoring system, routing and simulation, and it's like the general methodology that we have with some little change about the specific parameter. And at the end, interactive streamlined leaflet web app. Let's start. What is it? This 6-term scoring system. Okay, the first step for creating our model is data collection and processing. How we did this? I told you we had 2 types of parameter, basic and city-driven parameter. We collect this historical parameter from OpenStreetMap and Open Data Bologna for a more specific parameter, and live data that they were our dynamic data set from TomTom APIs. The tool that you use to implement this methodology, it was more with QGIS processing and Python and other software that in the next step you will see. Okay, modeling of physical system. Let's explain what is this thematic scoring system for Bologna. We had 2 important parameters. One, it was basic parameter. One, it was city-driven parameter. That for Bologna, for us, is very important. But how I was thinking, okay, how I can join and match these 2 parameters together and create a unique scoring system. So we end up to create this 6 safety thematic that, as you can see, we have almost 6 parameter: traffic exposure, infrastructure and safety feature, security and visibility, environmental, social security, and comfort. And at the end, giving the weight to all of these terms and creating our route. Just remember these 6 terms because they are very important for the next step that we have. So let's break down how we create this 6 terms as an example. I told you we had these 6 terms, and each of these 6 terms, they are include of our basic plus city-driven parameter, and each of these can have some goals. So as you can see, this chart, it just belongs to traffic exposure and speed, that we divide these terms to 3 parameters, that is 30-kilometer zone, ZTL, T-zone, accident data, and traffic data. And each of these parameter has a special question, and you have to calculate all of these parameters separately in field calculator formula and create a scoring for them. Let's give an example for traffic data at the end, how we did for each of these parameter scoring. For traffic volume, according to the traffic data and literature view, we have some number for volume. Means if they have high volume, they have number almost 20,000, and this 20,000 is belong to type of the street. Means motorway, trunk, and primary always, because they have a lot of traffic, cars or whatever, they always have a very high volume of traffic. So the number for this kind of street is more or less 20,000, 50,000. But instead, for pedestrian or footway, that they are very lighter, they don't have traffic, the number of the volume is almost 10. So almost they don't have any traffic. So we gave to our machine, to QGIS, this data according to our parameter, as you can see, and this QGIS divide all of our street according to the type to their volume, and as you can see in our chart, we have 2,110 whatever is belong to each street that we have. But we don't need this 1,000, 2,000 or whatever volume. We need a specific number that is 0 and 1 to compare all of our parameter with just those numbers. So the formula that we use to convert this volume to scoring, to normal scoring, it was this formula. And as you can see, when you put, for example, footway that has 10 scoring of volume, the score was 1. Means it was perfect. It doesn't have any traffic. And instead, motorway that has the volume 20,000, the score was 0. That it means it has a lot of traffic, and all of our parameter just converted to 0 and 1, and it's understandable for the machine. Okay, at the end, the visualization for the city of Bologna for traffic ended up with this map. As you can see, we one by one we calculate the scoring for all of these parameters, and final number of scoring for traffic. Traffic was averaged between zone, accident data, and traffic data. And as you can see, in the center of Bologna, that we have ZTL, that we have the restrict of traffic, and it's historical. The number are near to 1, and they are green. And outside of the city, they are red, and it's showing them proof of concept that our analysis it's right. So. But we need to understand this situation around each of these schools. How we can understand the situation, the traffic area that we have for our school, what it is. And we need to get information about routing around the school. So the way that we did, we create a buffer almost 300 meters around each school, and around each of these buffer, we had our segment related to them scoring traffic. So machine can understood, okay, the center you had less traffic, so the school has in a green zone, and the other one maybe it's red or orange or whatever. So we create a ranking for each of our school according to the traffic. And we did this all of this step for all of these 6 parameters, 6 terms that I told you. And I just put some brief screenshot for all of this, that showing the process, how they react. For infrastructure scoring, that it was average between bumping, crossing, sidewalk, biking. For visibility, that it was average between lamping and signal. For environmental score, it was average between green and air quality. And social, that it was bus stop and school accident. So Step by step, we understood the situation of our 6 thematic cores around the school and for the city of Barcelona. But at the end, we have to know the overall score for the city of Bologna, how it is the final score, the final safety score for city of Bologna. According to the European Transport Safety Council and WHO, traffic exposure and speed and visibility are 2 important thematic or parameter that can affect on the safety of the school. So we gave them more weight as a priority, as an important thing to calculate our final score. And finally, our final score, according to the data that we calculate, is this visualization that's showing that final score safety for Bologna is more or less between 0.65 and 0.75, that you can see. According to our data analysis, the situation of Barcelona is not bad. It's more or less near to 1. It has a good foundation, a strong baseline of safety and comfort around the school. So, but what about the weakness of the city? All of the number under 0.65, you can call it as a weakness and vulnerable zone for our city. That planner can see not just how bad the situation is, but what kind of intervention you need to do for your city to improve the situation of city. So according to this, we calculate the weakness of our city, and they give us some weakness value and which kind of parameter are belong to this weak value. And you can see in Bologna, it's more related to traffic and environmental, that the planner or city maker can understand, okay, the problem related to city is based on the traffic and which zone of the school we have to improve this situation, and they have the real plan to do the action. About the cost, but okay, we understood the weakness of the city, but what about the cost proxy? This cost proxy is some proxy, is not really cost, and showing you how much effort you have to do to solve the weakness, the problem that you have in your city. And we calculate this one with this formula, and the visualization around each school, it's from 1 to 1,000, that it means you have to do a lot of effort. According to this cost proxy, we also give some ranking to the school that they need priority to do fast action, and they have the worst situation in the city of Bologna. So the second step is understanding the routing. Yeah, for sure. Yeah. And that's it. It's related to creating a networking and passing this data to the network, and creating our routing according to the safety and distance. And we create four routes. The current route scenario is more safer, and balance is longer, safer, and improve. We just change some parameter in our city, the weakness of the city, and we create improvement in the city. And you can see the key parameter and compare of our key parameter between scenario, improvement, and balance. And you see the scenario one is the best option, and the cost is less than other one. And at the end, we will
leave it. We'll show it.
No, it's just fast. What is it? Can I cannot open it.
It's okay, just move back to the presentation. We have to, pretty much, we have developed the web applications, then we have videos of it.
I don't know. This doesn't open it.
That's okay. Right, sorry. We're gonna, it's okay, leave it. Pass it to Danny.
Show it 1 minute.
It's okay.
Okay, 10.
To conclude, the main achievements of our project are we could demonstrate the replicability and adaptability of the UDT we developed through 2 city models, and we identified the unsafe school routes and simulated interventions like crossings, lighting, traffic calming, etc. And we provided a decision support tool for municipalities. Okay, the effectiveness of the UDT. Okay. This framework works with both simple and rich data sets, and the feasibility can be identified because we used open source data, open source tools like QGIS, PostGIS, and PG routing tools. We could test the scenarios and see the improvements even before the real-time application, and we could identify the exact and safe road segments. Coming to the economic impact of this project, we considered accident reduction cost and CO2 reduction cost and long-term health benefit cost. In accident cost, we considered medical cost, human cost, and administration cost. The CO2 reduction cost is around 80 million for each cities, and the CO2 emission for each cities were identified using Weldometer. The health benefits are comes from the improved active travel modes, and it reduced healthcare cost by reducing asthma attacks and okay. Coming to the sustainability impact, we have social sustainability. We have achieved social sustainability and environmental sustainability. Social sustainability is achieved through improving accessibility, safety, and equity. And it aligns with the EU's Vision 0 to 2050 and UN's SDGs. The SDGs achieved are 3 by improving health, 10 by reducing inequalities, 11 by supporting sustainable city developments, and 13 by climate actions. Environmental sustainability is achieved by reduced CO2 emissions. Coming to the limitations of this project, there are some data gaps that exist. Missing of behavior, children behavioral models, because it depends on children's preferences and group dynamics, and limited stakeholder participation and prototype risk due to governance needed for long-term use. By integrating live sensor and traffic data, the data gaps can be addressed to an extent. Adding child-specific mobility models, developing a VR or AR route testing for more interaction, and expanding it to more cities are some of the expected proposed future works.
Can just push this one and show us very fast the.
Okay, this was pretty much our presentation. We know we took a little bit of time. So questions? Right.
Why it doesn't show it?
Thank you. So Mathieu had to leave for a short time. So who wants to start with questions?
It doesn't show it.
You gotta
I can start with the questions. You mentioned about data cleaning and harmonization.
Yes.
What was that done by hand?
Yes, initially it was just to be able to understand how the system would perform. But when we move towards the back end integration and optimization, all of that information is being done through the coding. So whatever data you throw at it is going to be able to do that.
Okay, because the other question was how you would scale that if you would have to do all that manual labor at the beginning. So if you have to do that for each city.
Oh, you meant the data cleaning part?
Yeah, yeah.
What we've done, we've utilized, that part is not automated. So what we've done, we've run Python scripts to be able to identify what types of errors we had and what missing information we have. And then we took it individually and compared with different data sets to see if we can actually fill them out or we have to filter them.
I cannot.
And my other question is about the weights that you were using. Would they be changed from one city to another?
No, because the way we've left it in this situation, as you've seen in Bologna, it was a very particular case where we've analyzed the city and the city has its own specified weights. However, in Barcelona, we wanted to give it more freedom to the stakeholder policies that they can prioritize their weights depending on the, I would say, dimension of safety in terms of parameters they would prefer. That way they have complete freedom to pick what types of safety they should consider based on their parameters.
Okay, so what's the strategy for you defining the weights?
No, Barcelona was more general and it was like a test bed for our methodology. And as you see, the data that we gather for Barcelona, it was more general and basic parameter. But for Bologna, we try to implement exactly the methodology, but with a kind of different vision of parameter. And we give this chance to also client if they don't want this big a big architecture for implement their digital twin. You have other chance that is cheaper and that it's more economic for to implement your digital twin and even can be more precise if you have your data driven parameter in your city. So we gave these two options as a choice to our clients, and both they are flexible, means that you can at the beginning I told you they are like a module. You can transfer both my project to the to Bologna to the Barcelona and implement all of the data that I have in Barcelona. But we wanted to try new way. It didn't make sense you again replicate the new project with the new city in the same way because we had it already. We gave more chance to our client.
Okay, thank you.
By the way, I couldn't show the application. It was interesting. I don't know.
Okay, I will follow this question because you mentioned your clients, and then maybe it was because we should cut some corners in the end. That who would be your clients in this case? So urban designers, municipalities, or general public, or who would you design this for?
I mentioned because we try to also focus in our weakness and vulnerable zone in our city. So this one, it makes sense for city makers and decision makers to do action according to the plan that they see or the problem that they can solve for the city. And it's better for doing action actually.
All right. So because it can, so with these kind of simulations, you can highlight regions also which has issues and not just highlight which parts are the best for any kind of user.
We did, yeah.
What we've done, we're able to introduce modules to be able to simulate specific types of interventions and see how safety would change, right? Therefore, saving the council the money to be able to actually implement those policies or interventions that they want and figure out, oh no, they don't work or they don't work as well as they would expect, right? That was the main idea behind the simulations.
So basically, if you do the inverse, the inverse of any simulation, you will see which parts are not really a good choice. And in this case, the municipalities can act.
Yeah. Because we figure out the final safety score for the city that has a best situation, and under this final score, of course, is our weakness about city. So we give a chance to a planner, to city maker, to a stockholder, whatever that is related to the city, municipality, give it this chance to them to understand the weakness around of our school according to the parameter that we gave a value to them. And for example, they can understand, okay, infrastructure, we have problem in crossing, they can improve it. In traffic, we have problem outside of the city because all of the scoring in this area, they were lowest score. So it give a good plan for them. And actually, we put ranking for each school according to this parameter that we had and according to analysis that we did. So everything for them is clear right now. You just need look at the web that we create for them and understand the situation.
So to summarize it quickly, yes, it's a multifunctional platform that can provide as well the evaluation of your current city, see how your city is performing based on the parameters that we've described, but at the same time, implement the policies and analyze their consequences.
And would this service be available for public? So, or generally just
It can
as
be
an inside
some
use?
functionalities. That's why we've built it modular inside of Barcelona. Some of the routing, it can be, because as data comes in and the system updates and evaluates himself, the routing part, it can be available. Just the routing part can be available to the public, right? So they would know exactly at that moment in time what would be the safest or their preferred path to take their kids to school. The rest about the simulation, that would specifically be for the council itself.
Yeah, because at least in our country, this kind of data information transfer would be really tricky. So to know outside where are the major accidents, to know what areas have more, I don't know, higher criminal rate and etc. These are kind of restricted and,
Yep.
and not available for
We had
public.
this problem as a limitation also.
Yeah, I imagine.
Yeah. But finally, with some simple simulation, you could understand the basic information about weakness of the city and problem that you have in your city. Is not difficult because all of this information, they were available and we could use them.
So in my opinion, I think that what you've done is a bit even more general than just safe routes to school. It's safe mobility in some sense. So is it just restricted to go to one point to a specific school, or can you do any route planning across the city from one point to another?
Any point, because what the input was from the user to select the starting location. That can be either selected via the map or take your own coordinates, for example, to your application you're using it from. Then you can select a point exactly where you would like to be routed based on those types of safety features. In our instance, because it was ARU and we worked to create safe routes to school, it was just to guide you to all the schools that you would select. But the switch in between, for example, a school or a gas station or anything else is just a matter of a switch.
Yeah. Okay. So maybe one issue I have is that, or at least one question I have for you is how do you validate your all your choices, all your models of giving a specific score to this aspect, then weighting that together, etc. Do you have a quantitative way of validating your approach, or is it just based on a qualitative look at the street map and saying, okay, this makes sense? Or...
No, it was actually validated through the existing safe routes to school that it had. Even though they were not widely available, we were able to identify the policies that I would say I don't want to see the policymaker or the expert into safe routes to school they've done, but they have been evaluated against some of those criteria. Because at the end of the day, it's a mixture between what we understand to be the safety from those parameters and what the experts they would say.
And when you choose a specific formula to giving a score to, is this based from the literature or?
For example, for my part, it's related to field calculator for commuting the number for
QGIS, means they are available. If you want to give a traffic score, it's this formula is available. It's like a mathematics. You have it in your QGIS, and you give this formula to QGIS, and you give the score to your route, your segment. So yeah, go.
Can I add to that?
Yeah, sure.
So for example, from the pollution data sets that you guys have seen, what we've done, we've actually take the actual values from the World Health Organization, what is described as being the safest condition in terms of pollution, and what would be the European limit in between to be able to calculate those safety scores. So those type of kind of logics we've utilized when we are creating the calculation for the safety of the school for every street segment. And we had to normalize it as well, because we tried to compare parameters as well as we're applying weights and importance to that specific data set from a policymaker point of view. We had to perform the normalization as well based on the criteria that we were able to find through the article.
Okay, thank you.
This is our application that is showing all of this data that we already.
Any other question?
You take off if you like it.
So if no one has questions, thank you again.
Thank you.
Time for? Okay. So maybe we'll take 5-minute breaks, and in the meantime, the last group can prepare.
Yeah. They're fine. Okay, I'm here.
Yeah. That's the current. Okay. Video. Okay.
Yes, yes, we are.
It'd be nice to, but we get
So try to stay on time.
Yeah, yeah, we will. The trial session. 35 minutes.
It's just the time for questions.
I think I really want to show them. So we don't find yourself at the time. I think it's a great word. To be, it's impressive, like on like there's the like past months. I mean, from what we saw here, that we able to do is the protocol. So don't worry about like this. I know this is stressful, but really, like 30 seconds more. That's the least. The ways that everyone like created about the same how they want to hear more about probably storytelling the way expressive the data, software application, the and then also don't go. Wider outcomes. So I think overall, yeah, we tried something. Yeah. That's why you're probably I think solution. So it's much better than the video. And I think I can compare this. That's good. That's the game. So I do that. That's more yeah.
Is everything working there?
Okay. You put the picture with this. Okay. Like you take the picture with this. The other people are taking pictures of whatever slide. Okay. You just
Is this working?
Yeah.
Okay.
So I will just hide the thing on top. I can. That's okay.
Okay.
I let you introduce.
Okay, perfect. Okay. Please all, let's continue with the last, but not the least for today. Now we're going to see this digital twin for a road tunnel for operation and optimization, in which Ayesa, which is also one of our companies from the beginning, has helped us, and also Manolo from the UPM, and I think it's going to be very interesting. So the floor is yours. Thank you, guys.
Thank you. Hello. The name of our capstone is Digital Twin for a road tunnel for operation optimization. Our group is four by Hossam, Fem, and me, that I Anna. We are going to follow the next contents. The first one is the introduction, then problem, solution. We have developed two models of machine learning. One of these lighting model and another one traffic model. Then we have developed the machine learning integration with SCADA, and we have the conclusion. As I said before, I'm Anna Sena Hossam. Our academic supervisor is Manuel Romana, and our company supervisor are Fidel San Emeterio and Carlos Rodriguez. First of all, we want to explain the roadmap because we have followed this roadmap along the project. The first thing we have done is the reality capture and BIM, in which we have developed the 3D model in infrared and civil 3D of the tunnel. Then we obtain the data and we evaluate all the data that we have and the needed that we have, and if it's important or not, using it for the input for the model. Then we develop the machine learning model, then the integration with SCADA, and we have finally explained future enhancement about this capstone. We want to mention work plan and schedule because we have the data in June of 2025. So from this time, we have developed the most part of the capstone. Before of that day, we only can work in a state of art and something like that. The tunnel that we are going to, that we have developed is the Túnel Mellafanega. It's located in Seville. It has two parts, but we only developed one part that is 80 meters. It's short tunnel, but the other part is shorter, so we don't take it into account. It is managed by the Ministry of Transport, Mobility and Agenda Urbana in Spain, and it has 2 and 3 lines per tube. Also, to develop this digital twin of the tunnel, the first thing that we have to do is to know all sensors and all equipment that the tunnel has. This is the all sensor that we have used in the model: CO sensor, opacity, anemometer, temperature, traffic flow detector, luminance, and the SCADA.
Okay, as you saw before, the SCADA records all the data that you saw here. And in the figure, you can see all the different type of data that the SCADA system records with the various sensors. And we obtained 5-year data starting from 2020 to start of 2025. And the data we have used are wind speed and direction, luminance, carbon monoxide, and opacity inside the tunnel, and also the traffic information inside the tunnel. These were in PDF formats, and we extracted them into tabular format. So, Osam, please mention the problems.
For problems, first of all, this tunnel is being developed by IESA in collaboration with the Ministry of Transportation in Spain. So somehow the problems inside of the tunnel has been provided to us to work on them. The first one is the lighting optimization. The current format or the current setup of our tunnel is that they have inside of the tunnel a very old lighting system. This lighting system is being operated through lighting sensor. These lighting sensors are being installed outside. Because of the area and the nature of this area, there are a lot of clouds. These clouds might cover the sensor and might make some interruption into the operation. And because of the lighting system, as we said, is a little bit old, so the lighting system needs some time to cool down and start again. While at the beginning, we might think this is a very simple problem and we can solve it just by like some of the mechanical system, like covering the sensor or making some modification to the way that the sensor is working with. But for the research intent, we choose to continue with it, okay? And sometimes like great things come, let's say by chance, but in our way with diligent work. Second thing, traffic flow prediction, which Anna will speak about it in details. Okay, and this target, it has been introduced in a different way in the beginning. It was ventilation optimization, but with time, we choose to change it to traffic flow prediction, and Anna will speak.
The principal challenges that we have found in the traffic flow prediction are the following: temporal dynamics, because the traffic volume varies by the time of the day, week, season, or maybe if it's holiday. Because there are special events like concerts, sport game, holiday, etc. And also because of the population growth, we can see in the data that the traffic volume has increased in the last year. Also incident and road works, because incident also can affect of the data, because you don't have the same quality of the data if there are incidents inside the tunnel. The vehicle type, because if you have more truck inside the tunnel, the volume of traffic is not the same. And also the API challenges, because we want to use another traffic data apart from the detector that are inside the tunnel. But for example, TomTom was very challenging, because it can traffic intensity based on the flow duration. So we cannot use this external source for develop the machine learning model of traffic flow.
For tunnel lightning, putting more on top of what Hossam said, according to the tunnel inspection report, the hardware is severely damaged because of this rapid toggling of the lights. So we will design a new system which will guarantee driver safety, minimize the energy use, and mainly reduce this unnecessary switching in compliance with the necessary regulations. So when the drivers go into a tunnel, they face something called a black hole effect. So the outside luminance and the portal entrance luminance has to be in similar values. But currently, when the cloud passes, or anything that casts a shadow on the sensor, makes raw luminance spikes. And because our tunnel has HPS groups, fixed power steps in the lamps, so certain circuits are on or off. And when these spikes cause regime changes, there are high install loads on the electricity system also, so it can cause voltage sags. And this frequent reignition shortens the lamp life. You can see in this table the typical activation ranges, operating times, and the lamp counts that are opened in certain regimes. Regime can switch between the clear sun and twilight every 5 minutes in a cloudy day. So we propose some solutions to these problems. First is a machine learning based lightning control, which adopts a safety first mindset, which will be self-adapting and which will avoid needless toggling. So we will fuse together sensor data and forecast data, weather forecasts, make a prediction with the machine learning, classify the regime change events, fuse it together, and select the regime correctly in the SCADA without unnecessary toggling every 5 minutes.
Okay. For traffic flow prediction, the solution will predict the congestion before it happens, allowing operators to take preventive measures, speed limitation, the total dynamic signage, and something like that. Enable better coordination with surface road network to reduce bottlenecks and tunnel entrance. Predict inside health, detect a normal pattern that may indicate incident or load stage. Our model can be correlated with a ventilation model because the traffic flow have a high correlation with ventilation with CO and with CO. Traffic flow forecast can help schedule maintenance because if there are low traffic, the maintenance could be better. And real prediction feed travel information system can allow drivers to choose another alternative route.
Okay, so I will explain the process of building the lighting model. So we have, as we mentioned, in the entrances, 2 luminance sensors. These are measured with photometers in terms of candelas. And this is a typical week you see. These show the maximum, minimum, and mean readings of the sensors. These are recorded hourly and in a 5-year span. So as the operators mentioned, the main problem was, according to them, the cloud cover. And the cloud cover, they suggested that causing this flicker. So what we did is, in every row of the data, we separated the cloud cover percentages that we gathered from the open source data into cloud cover bins. And then we put took the difference between minimum and maximum values of sensor readings in an hour. And we tried to see if this difference in readings, minimum, maximum, which we call spread, is related to cloud cover. And as you can see on the right graph, when the cloud cover is 0 and 10%, the difference is almost non-existent. And on those days, which is similar to the first peak you see, there is no problem at all. But when cloud cover is present, especially like in the range of 20 to 60, 70%, which is when the weather is partly cloudy, this causes a lot of difference between sensor readings in an hourly mean. Furthermore, we check the data we have in hand to see if it is going to be useful. On the right, you can see that seasonal curves are as we expect, because in summer the readings are higher relatively rather than winter, and the daily curve, which is the average of all the data we have, the peak sits between like 12 a.m. and 1 a.m. and there is no skew to left or right. So we think that this data might be useful. Then we introduce in the meteorological variables that we gathered from open source variables. The first one is the weather code, which is a dummy variable, like 1 for sunny day, 0 for cloudy or foggy. Then we get precipitation, and most importantly, cloud cover values, which is in percentage. Total cloud cover in the low, middle, and high elevations. Wind speed at 100 meters. This variable is important because when there is a wind, the clouds are moving, so shadows are changing. We also got solar radiation variables. And as you see in the graph, actually most of the solar radiation variables capture the peaks and drops, some of them, not all of them. So we thought also these variables might be useful in our model. To help our model understand the time geometry and position of the sun in a day or in seasonal changes, we have introduced some variables. Also for hour of the day and month, we have included dummy variables. And for cloud cover, we like cloud cover total, low, mid, and high are just the variables we got from the open source data. Then we introduced cloud cover lag 1 hour, which is we shifted back the data, like what was the cloud cover like 1 hour before, and what is the rolling median of the cloud cover for the past 3 hours. And then what is the difference, like D cloud 1 hour is the differential, is it increasing or decreasing? Then also, as I mentioned, we have solar radiation variables, weather codes, precipitation, and shortwave radiation. Because this system will run in real time, we can also use the sensor readings of the past hours to understand the momentum and detect any change that has occurred an hour before. In total, we have 27 variables. We have cleaned this data, removed some portions. There were no readings in some portions, and we will try to estimate the mean sensor values and try to predict them. So we have on the orange side, you say a 90-day split, which we will test our model. And the rest, we have separated 5 faults. We trained on them differently and validated on the 90-day split at the right. This data is in time series. So we also tested and trained it in a time series manner, because if we just scatter the data, then the system knows like future readings, so it tends to overfit when we did it like that. So this is our strategy about testing, and it also mimics the live operation. I will first talk about the different models we tried, but generally the boosting trees dominated, and like GBM edged out a little bit, but all the models converged together. We expected this because most of the variance is explained by the variables we have, and they have a little headroom to improve. So because we chose like GBM because it edged out, and it was took half the time to train according to the other models. And the error we have, root mean square and mean absolute, sits between the range 7 to 4%. This is a look at the predictions we had with our models. Now, what is it all for? We use these predictions to detect if a unexpected drop occurs and the system requests a regime change. We can classify it as a sustained or not sustained drop. If it's not sustained, then we don't have to change the regime. But if it's estimated to be a sustained drop, then we can change the regime accordingly.
Okay. Firstly, I want to talk about the CO model that we don't have developed, because this was the first model that we tried to develop, because it's the most important inside the tunnel, the CO levels. But when we trying to develop and we see all data that we have, we see that the most of data of sensor of CO are 0, and the only peaks that they have is because of maintenance. So we cannot use this data to develop a machine learning model. This could be because the piston effect in the tunnel, because the tunnel is very short, the vehicle move the air, and they don't produce CO inside the tunnel to make sensor make alarm in the sensor of CO. To see more data that we have, we take into account that there are a high correlation between traffic flow and CO sensor, as we can see in the graphic. So we decided to change to develop a model of traffic flow prediction. We have this input for the traffic model. We have some value of the sensor, also of temporary that Sam has explained. Lag, some lag that we think that are important in the future, in the forecast for the traffic flow, and some rolling range and rolling absolute range. This I'm going to explain then because we have choose a catbus model, and this show the importance of the variable, and with this graphic you can choose or remove the variable of the input of the model. We have developed 3 models to compare. Catbus and Lighty GVM is very similar, but we decide to choose a Catbus because we have a categorical feature as input, and this model works better with this input. With all data, we have separated in 2 parts, as same explained, because we have in the same line one hold out of 90 days to make a honest test, and the other data we have 20% for the test and 90% for the train. As I mentioned before, we use a catbus regressor because of the categorical feature and the high predictive accuracy, and because it's fast and efficient. This is the result that we have obtained, that very accuracy result. Also in the graphic, we can see the traffic, the real traffic and the predict traffic that are very, very accurate. Also, we have showed some graphic about the errors, because with this graphic we can detect is our model work well or not. First graphic show the absolute error. Most of them are less than 100, and that's good because the traffic volume is around 1,000, around 2,000. So it's good, but we can see that there are some outliers, around 700, that we have to investigate because it could be maintenance or some days of holiday or special event that the model doesn't follow. There are 2 more graphics, scatter, where we can see that most of them are aligned with the diagonal, and the histogram of error, that the most of error are around 0. To avoid these high errors, we want to include a new variable is close to holiday, because we detect that not only the day of holiday is important for the traffic volume, also the day before or the day after, if the holiday is in weekend or in a bridge. But the model don't see this variable with importance, and we think that we don't have enough data with enough information to detect this variable with importance.
I can still remember the first time we have a discussion with Professor Romana, when we start to speak about tunnels and what are the problems. And I can remember when he said that one of the most important things is to try to make a simulation when there is an accident inside of the tunnel, or at least to prevent to have any accident inside of the tunnel. The tunnel is already in place. The tunnel is a critical infrastructure. The tunnel is being operated by SCADA, and it's already, as we said, in operation. So our scope was, after what Jim did, what Anna did, or in any other tunnel similar to this. By the way, this is a pilot project for IESA, okay? What shall we do after that? How to integrate our solution or any other team solution with this tunnel? How to integrate the AI with the current SCADA from, I don't know, maybe 2018 or even before, okay? Our focus area was to integration of machine learning interface with real-time SCADA operation, safe actuation based on validation prediction, use of external APIs, because Without APIs, we don't have a machine learning model like what Jim did and Anna did. And continuous feedback loop for retraining and audit. Because right now, if we just did something without investigating the result, seeing what are the updates, we did nothing. And our solution was found in OBC UA. OBC UA is a protocol. This protocol is coming with the modern SCADA system. It's allowed modern SCADA system to integrate with AI. So as you see in this architecture, we had the idea of making an external client. This external client can be integrated directly with SCADA as plug and play piece. Okay, and it's coming from different layers. One of them is the data collection through the data coming from the tunnel and, the data coming from the tunnel and the API is coming. These data should be go through data bridge and middleware layer, where OBC UA client will react, and then an ETL engine will transform the data into what we need for our machine learning algorithm, and then a streaming buffer to make sure that the data is coming to the machine learning layer in a continuous way or as we want according to the AI. And then we have here the machine layer interface, which will host the models and making a decision engine and getting an output. But this output will not be fed directly to SCADA. This output, first, it will be filtered. Okay, it will be filtered according to the threshold of SCADA that's already hard-coded inside of SCADA. Okay, if it's within the range, it will pass. Not within the range, it will be like let's be cut it out, and SCADA will be in place. At the end, we have the monitoring and feedback loop, of course, for keeping the data and for retraining the model and for even auditing what was happening inside of the tunnel during the operation. Let's deep dive a little bit. We have the data collection layer, real-time sensor coming from outside. We have external APIs. We have data routed through BLCs and collected via OBC UA client. And we have ETL extracted transform load engine, normalize all input, both internal and external, for timestamp structure delivery. And then we have the logging and monitoring, centralized logging for raw tunnel sensor streams, external weather API, model input, output, SCADA set points, and responses, enable historical review and model retraining with hybrid data sources. And as we say, for safety during operation, we have fail-safe logic enforced before machine learning output can influence SCADA set points. SCADA remains the sole authority for actuation with manual override always enabled. Operational threshold are hard-copied inside SCADA. All machine learning actions are routed through a validation layer before execution, and continuous logging ensuring auditability and traceability for every inference and action. For cybersecurity consideration, we have this client in a separate subnet. Okay, this can be gapped, by the way, gapped, or can be connected to the internet through some protocols like API communication, encryption using TLS 1.2+, firewall and IB whitelisting to just make the used APIs for our machine learning to pass and anything else no, to prevent some kind of cyber attacks from outside. External data is subjected to schema validation and sanity checks. We are using OBC UA. It's protocol by itself and it's very strong. Security alerts triggered on anomalies or failed access attempts, regular patching and vulnerable monitoring on the edge environment and machine learning stacks. Okay, after doing this, without the financial and operation return of investment summary, this means nothing. It's just a concept without real touching the real-time exercise and real-time, let's say, stakeholders that wish to engage. When we did our exercise in the market right now, we found out that we can invest approximately about 7,000 euro per tunnel, and the recurring annual cost around 2,500. This cost might be for maintenance, for APIs and machine learning updates and model updates. At the end, we found out that we can make the system yield estimation saving exceed 3,000 per year, but not only, of course, for this reason, it's a cumulative reason. One of them is 15 to 25% reduction in energy customization. Consumption of lighting. And if we can do this, we can, instead of having a team dedicated for each tunnel, we can have one team dedicated to multiple tunnels. Of course, this has to be studied, had to be validated in real life before achieving it. But if we did something like this, we might save about 40,000 per year in manpower. The system achieved full payback within 3 months if we are calculating our payback and ROI based on these parameters. As we said in the beginning, we did this for the sake of research, but actually what we found that it's not only for tunnels. If we got the availability to implement this, it will be implemented for any SCADA system that we have. And we have in Europe a lot of, like, let's say, places and a lot of systems being run by SCADA. Like, for example, we have energy and utilities. We have more than 3,000 power plants, millions of smart grid nodes. Like we have SCADA everywhere. And we have in transport, we have more than 354 tunnels in Spain only, 1,000 across Europe. Me, personally, I passed through 3 of them in my way here. And we have a lot of airports and metro and rail networks. Everything have SCADA in it. And once SCADA is being developed after 2008, it's OBC UA as per the standard of manufacturing. So it should be AI ready. We have water and water waste, like the figures are really clear. And the drivers are 2 main drivers. One of them is our main subject here is the digital twin, with more than 40% in CAGR. And SCADA market may be less humble compared to digital twin by 7%.
So we have talked about many things, and to summarize and sum it up, we have collected the data from SCADA, fused it together with weather APIs. We did exploratory analysis and saw trends. Based on them, we developed 2 models, validated them, tested them on the test data sets, and we set a foundation for future integration, we believe, and made a big step towards real-world application that we can integrate these systems into many tunnels around Europe and around the world.
For future enhancements, we got some future enhancements that we can develop, like remote supervision and control, that we can, for authorized user, that can remotely control tunnel system through an encrypted web interface and OBC UA write back. Multi-tunnel data analysis. We have a lot of tunnels and we can collect all the data so we can present these data in a good way to the decision maker. Readiness for more use cases within life and historical data from both internal and external sources. The configuration makes it possible for other use cases like predictive maintenance and AI work optimization. One more thing that we got through our interaction and friction with this project, that we didn't find, let's say, an emulator, okay, that can support multiple systems. For every producer, there is a single emulator, but there is no emulator for companies that are making development and are making design to test what we are seeing, or even to give some kind of scenarios. This is a critical infrastructure. We have a lot of critical infrastructure, and we need something like this, an emulator that can test multiple interfaces and the AI from different vendors. Thank you.
Thank you very much for the presentation. Who wants to start with questions? Okay, so I was wondering on the lighting model, when you showed the test, when you showed the performance of the model, was it on the, yes,
This
the
one?
prediction results? These are on the
90 days.
90 days that were left out from the training? Okay.
Completely unseen data.
Okay, okay. And so we see sometimes that the maximum values are always a bit more difficult to catch than the low ones. So do you have ideas to further improve?
Well, when I look at it, sometimes, like you can see here, this is but that's due to lag of the cloud cover coming up and down. The shadow comes and goes, but the model generally tends to predict like this, so it generally misses these big peaks. My thought of it was that because the station that these values are measured are far away from the panel itself, like not exactly same location, and the angle of the sun also changes. Like if we have a temporal encoding in maybe GIS or something like that, if we build upon it, then we can maybe catch these peaks, but we don't know the exact location. We know the location, but we don't have the angle of the photometer, or we don't know where it's looking at that time. And at the entrance or the exit, is it facing like east, west? Maybe those variables can change it, but if you look a bit further, it actually predicts a little peak there, because we have used the previous hour's value, sensor value, and used that to actually catch those peaks, because in the beginning, all the values predictions were very smooth. Like it didn't catch any peaks, but after we included the cloud cover values, it started to get some peaks and drops. But yeah, of course, it can be improved, but these are my ideas.
And did you consider using machine learning models that are made for time series?
Well, we have tried, but they didn't yield better results.
Okay.
And I have no idea why.
Yeah, with machine learning, you don't always know why. Yeah. So, okay. And on this topic, did you try to quantify how much you would gain in terms of energy saving with the switching on and off, etc.?
Yes, we did, but I don't have them right now in the presentation, because we had a lot of hard time deciding on changing the protocol and how do we quantify what is considered a sustained change and what is not. And these have to be checked with the safety regulations, and we also need further and deeper information on the tunnel operation system and the SIVA, which is the current software. But we like 56%, more than 56%, we have reduced the toggling, because we don't change the regime when there is a dip that we know is going to happen, or also when there is an unexpected dip, we keep the regime, and when we try to simulate that, it's not very correct, so we didn't include it in the thesis or here, but it's logically correct. We have reduced significantly the toggling, which was causing the stress on the hardware, because these are HPS lamps, and as they told us, they need a certain time to reopen again. And these also cause safety issues, because when you close it off and the ambient brightness is high again, you can't open them up immediately, so there may be a safety problem in entering the town.
Okay, okay. And maybe one last question regarding the traffic part. So your initial goal was to predict the CO level in the tunnel, that's right? And you said that there's almost no data. That's
Yes, we have data, but the data are very small
Mhm.
and very similar. So we don't have a variability of data to know patterns or something like that. Only the day that is maintenance, the data go up.
Mhm. And I was wondering if there's no maybe very simple model in the literature, given the amount of traffic in a tunnel and maybe the size of the tunnel, just some very simple physical-based model to predict a very crude estimate of CO level. Did you look into that or?
Yes, we think that the CO model is more important than traffic model, for example, because also you can manage the funds. For example, if there are some fire inside or something like that, is better. But we think that with this new model of traffic, you can develop another model that you can predict CO, but not in this tunnel. You have to have data of another tunnel with more variable of data of CO, because in this tunnel is not possible because CO is almost time.
Okay, so you would use data from a similar tunnel to train the model and then evaluate on this one. That's what you. Okay.
In this tunnel because the data.
Yeah. Okay. Okay. Right. Thank you.
Okay. I have a couple of small clarifying questions. So you have showed us lots of different kind of data in the beginning. How much data could you use actually? So what was proper information for you?
We have examined all data.
Yes.
But when we have this all data, and we examine all data, but when we are developing the model, we choose some of them and we examine and eliminate time that we don't have data and something like that of the data that we have to use in the model. That is the question?
Just because you have mentioned that some data, for example, the traffic, that some data weren't really versatile enough, or there were some type of data what you can't really predict. So when there is a change in the large change in the traffic, if for example there is a special event or something that's are harder to detect. You deliberately said that earlier.
If I understand well, that's because the data that we have is 5 years only.
Yes.
The historical data. And in this data, we don't have enough pattern to develop. For example, what I say about the close to the holiday is because in this period of 5 years, we don't have pattern about the close to holiday days to have traffic volume.
Okay, so you had, because in 5 years, there must be lots of days before an event, but to build up a model, you didn't have enough from this type of data?
Can you repeat, please? What you say? I don't understand.
So, because in 5 years, there should be plenty of holidays and there should be plenty of days before the holidays, but to build up a model, you didn't really had enough of these? Or
Secondly, as we mentioned that in the beginning, the main target was to calculate the CO of the tunnel. Calculating the CO of the tunnel was a very challenging target because, as Anna said, that we have a lot of piston effect because of the cars. So one of the parts to calculate the CO was to calculate the traffic flow. Okay, it was one of the factors that we will use to calculate the change in CO. So we did our due diligence, but for there was no change in the data. That's why we came up to this part. And because we got the data, as we said, in June, okay, and after the manipulation, after the cleaning, after all of the stuff, to make like a proper investigation and a proper work on the data, we need more time. Let's put it in this way. So when data said that there wasn't enough data, she meant there wasn't enough data for the CO. Okay, but of course, with what we have, if we have the ability to identify more problems or to deep dive on everything related to the operation, we will we'll make use of all of these data to solve other problems that might be not identified by the operation.
Okay, thank you for the clarification.
Okay. From my side, just a couple of questions in terms of I want to know your opinion. In order to put this type of systems autonomous, what do you think we are? What are we lacking? Are we lacking more data? Are we lacking more safety factors? What do you think we will? How do you think we could put this as an autonomous system?
Okay. From my humble opinion, that it can be the identification of the problem, can be one of the team responsibility. It should be some kind of collaboration between the team and the data science and the data engineers to study the data and to check what is the real problems inside of the tunnel. Okay, operators, they will identify the visible thing in front of them, but data scientists and data engineers will go deeper and will identify what is the real problem there. One more thing that I see it's really missing a lot of saying, I am a BIM manager. We have something, the open BIM to to govern all the data coming, okay? But I didn't see something like this in action inside of the telecommunication and SCADA system. Every vendor has its own part, every vendor is working in a silos place. That's why whenever you are entering a control room, you will find a lot of monitors. Every monitor is checking something without the real integration between systems. Maybe Siemens has something that they are excellent, Schneider has another thing, but what about the integration between the data? From this integration, we can get something else. This integration is not there. We didn't find it. One more thing, that the designer will make the design for the system, okay? But at the time of integration, there is no sandbox that collect all the systems inside of the tunnel to make tests, to make scenarios, okay? There is no something like this. And unfortunately, for the academic part, we are working and we are getting data, and the vendors, they are working in different sphere. So these are some of the challenges that we can have.
Thank you, Hassan. And I really like you did a return of investment study. And with the figures you have, I think you may know that this is going to be implemented, isn't it? What do you know about this?
We hope so. We hope so. But as we say, this is like something to give us a light in the end of the tunnel, not media Faniga, but our stuff, that we can really do something with the integration of AI and SCADA, okay? And in Europe, we can do this in a very large scale with a very minimum amount of investment. And the return of investment is wonderful. But just we have to test this on the real world, because I believe that once we test this, we'll find a lot of challenges that need to be solved.
Okay, thank you. To add anything? Okay, thank you guys for your presentation then. And I think it's the last one, so
yes,
we can continue.
Okay, thank you all for attending. So Mathieu is still not available, so I'm closing the day for today. Thank you for being there. I don't know what's the schedule for tomorrow, but it will be in the other building as Mathieu mentioned. Okay, so don't come back here. It will be in building Coriolis. So not the one in front, but on the left if you follow the tennis courts. Okay, so see you tomorrow.
No.